Alrighty, can you hear me? No? Is it on? It's on? Okay. In case you're wondering, I'm not Christiana. She's, she's right here. She's the lead organizer of this summer school. We're really excited to have you here because we haven't run this summer school for 9 years now. So before Christiana goes through the introductory slides here, I'll just like to give a little bit of a historical perspective. So back in, it must have been late 2007, I was still a postdoc here at NCAR. Christiana, I think, had just left for University of Michigan to become an assistant professor. I just became a scientist one right after that, and then we decided to apply for funding here at NCAR to organize what's called the ASP Summer Colloquium. So back then it wasn't called DCMIP, that was a rebranding we did later on. At that time, it was a very exciting time to be in numerical methods modeling space because every major group on Earth was developing a new modeling system on, at that time, novel grids like CubeSphere, icosahedral, Voronoi grids, and everybody wanted a non-hydrostatic global model. And all of that was happening back then. And after the colloquium, I'll never do this again, but we put together this book here. Some of it is outdated, some of the stuff is not, but that was a really nice write-up of everything that happened back then. And it went through all the deliberations, well, not all, but a lot of the deliberations you go through to build a global model from a numerical methods perspective. Then for some reason, we decided to follow the presidential cycle because the next workshop was in 2012. That one Christiana was leading, and then it was 2016. Was that Paul Ulrich was leading it? And then if you add forward to 2016, you get to COVID. And Christiana and I were like, we really don't want to do this online because the experience here is really to interact with everybody, talk with staff, talk with your colleagues here, your student friends. So that's really important to us. So it's taken a while to find the money to organize a workshop or a summer school again. So with a 9 years break, here we are. The old format involved inviting all the major modeling groups on the planet. So ECNWF was here, UK Met Office, ICON from Germany, the Japanese groups, etc., and the major groups in the US. They were here for a full 2 weeks, everybody running test cases, and it kind of became competitive between the centers, so that was pretty fun. And if you notice, when you walk around at conferences now, where there's numerical methods involved, you will see DCMIP test cases. So they've really become important in the model development world. So that's pretty cool to have an impact on that. And I think that's all I want to say. So Christiana will walk you through much more formally what happened through the years and about the test cases and whatnot. So, but we're really excited to having here. So welcome to NCAR.
Yeah, welcome. Also, from my viewpoint, of course, you were in contact with me virtually via my emails, or I guess you saw the edits on the webpage. It's really fantastic to see everybody. As Peter mentioned, this is the 4th time we are doing it. And this is even, I think, the biggest group ever. I think we were really big last time in 2016. And here we are a group of 50 students and about 10 modeling mentors, so a group of 60 or so. Plus, of course, we have external speakers that add to that. So we are probably with that more like 70 or so. But the external speakers maybe not here every day. But you have a chance to interact with very prominent people in the community. And here, I want to also highlight that this is a very new version of DCMIP. DCMIP traditionally is about the dynamical cores as you know them. And dynamical cores, are the fluid dynamics component of weather and climate models. Some of you have even experience, as I saw from your applications. For some, it's maybe a new topic, but they're really the heart of a weather and climate model. And of course, then you add physics to it, you add an ocean model, you add land, and then in the end, you get a climate model. Yeah. So here we are really just looking at a specific component, the fluid dynamics component, and that is really the history of DCMIP. But This year, we were enticed to enter the new world of machine learning also, which is something we watch as, well, flying by even. It's really phenomenal when you kind of watch the speed of the development in the machine learning world in comparison to the speed of our model developments in DCMIP or the dynamical core world. So we do, and it's very experimental, but we do have an element here in DCMIP which brings in emulators that can emulate the fluid flow. And for the first time ever, we are trying to, intercompare a few. Not that we invented, you will kind of see this later today, we give an overview of the test cases and also the machine learning exercise. So not that we claim we invented the machine learning testbed that we are using here, but we are applying it in a new way. Also, I want to just highlight tomorrow we have a couple of nice lectures on machine learning, including today with Will Chapman here in the room. But tomorrow we really have the author of the idealized test cases online. He will give a talk, Ray Kakem from the University of Washington. And plus we have a representative from Google and NVIDIA here. And these are the emulators from these companies. These are the emulators we will be using here in the machine learning exercise or in the element. So I'm really excited about basically having you also meet the lead developers, I guess, of the emulators, or being here at the leading edge of that development. So I hope you have a chance also to interact with them, maybe talk to them at lunch if they can stay, and also ask them to maybe, if they could, just spend a little time with us here in the afternoons. The hands-on component is in the library here in the Mesa Lab, and the machine learning group maybe can enjoy their company, looking over your shoulders and giving you advice on some of the findings you might have. All right. Let me maybe dive into this slide deck. So this is kind of really, I just want to set the stage, give you a few pieces of information on DCMIP and add to Peter's comments. Let me kind of dive into this a little bit, and I prepared a couple of slides. Let's maybe start with that. I want to highlight that this is a real community effort, so nobody can do this alone. And this year we had a really large group of people. You see them all listed here, including a lot of people from my group. And I want to show them to you here in a minute, because without them, this wouldn't have happened. Yeah. So this was a true team effort, and they were so amazing. So yeah, congratulations, a team. Yeah, but everybody here contributed in unique ways. You see, people from Indiana University here, or mostly on the machine learning side, and you will see their faces here in a minute, and they have a chance to introduce themselves. We have an NCAR group here. We have a group here from Sandia National Labs. This is a Department of Energy lab, research lab. We have starting Wednesday, Colin Zaziki here from Penn State University, and also Dan Detzlich. He will come in for the afternoons for the hands-on session. He works at Colorado State University, which is just an hour away, actually, in Fort Collins. All right. Okay. Before we get going, this is not the normal way I would present my first slide. So topically, this would be super sunny and 80s. Yeah. So we are looking at a little bit of a mixed week here in Boulder in terms of the weather, but I am very optimistic that we still have a little bit of sunshine, especially I hope on Friday. Friday doesn't look too promising here, but we want to have an outside barbecue. This would be the Farewell Barbecue, which we cater here at NCAR. And NCAR, or the Mesa Lab, has a really nice so-called tree plaza, and it's so nice to be there. They set up tables there, and hopefully, if the weather holds, we will do it outside. If not, we do it inside, but let's maybe hope for that. I don't think this is really doomsday scenario. There will be thunderstorms, yes, and also there's a dip in temperature, yes, this week. But I hope you can also maybe in a dry spot go out, maybe see Boulder, see the hiking trails, maybe in the evenings, and just head out, which is a beautiful, beautiful place. Yeah? So basically, don't get discouraged by seeing that scenario. Typically, it's 85. So, righty. Oh, maybe one more thing. It is very dry here in Boulder. Typically, I'm not certain this week, so stay hydrated. That's a good piece of advice. We also have, of course, drinks, snacks here during the breaks, but there are also water fountains. Also, if you need, at some point, probably the bathrooms, I think they're the closest one a little bit upstairs. So you go up, actually, the little staircase here and head to the library, and you find signs for the bathrooms, right? Okay. All right. Also, this is, code of conduct. This is basically what we like everybody to follow. This is like good behavior. Yeah, be good citizens. Be respectful. Hear other opinions. Just listen to each other. I want to just kind of give you that as a heads up that this is a really friendly place. We are not doing any competition here. Yeah, so we are really here to help each other, and also that means you can help your peers. Yeah, we as mentors will help, but I know you have all kinds of experiences that you bring, and I think we will also benefit from each other as we go through the week. All right. What is DCMIP? Well, it is, as Peter mentioned, basically an event where we highlight the newest modeling techniques for climate and weather models. And this year we decided to bring back a couple of themes that we touched upon in earlier DCMIPs, but really didn't explore widely. And this was the impact of topography on the fluid flow in dynamical cores. So we have actually two elements, two test cases, or actually three, that will address that. And then we also actually go after another theme we had back in 2016, which was physics dynamics coupling. So the interaction between the fluid flow and rain, precipitation, like physics, that's called physics. And we do that on a really tricky small Earth. This is a feature that we really enjoyed doing or using in 2016. So basically we are able to shrink the Earth to really small sizes, and that allows us to get to non-hydrostatic motions and scales really cheaply from a computational viewpoint. This can only be done in idealized test cases, so don't try that with a full GCM. But here in DCMIP, that is really neat because you can just go after scales you would never typically resolve with normal compute allocations. All right, what it also is, well, it's a summer school. We will be meeting here in the mornings from 8:30 to 12:30ish. And then we go over to the library, which is just a little bit up the staircase, and then the hands-on session. It's a big space. There's power, there are power strips there. So bring your chargers as we plug in the computers in the afternoons. And well, for us, this is kind of maybe the educational component, but for us, it turns out it's also actually a research component. So we spent how many months, Tim? 6, 8 months. Tim in particular, others as well, Owen and Nicholas, you will see in a minute, designing these test cases. And that is actually fun, but also a lot of work. So we are not just repeating what we had been doing in the past, and we see it also as a contribution to the community, because we will be putting these out as suggestions what the Dynamical core community would be able to use in the future for their own model assessments. And this is what Peter mentioned, actually happening. So as you see publications in the Dynamical core world, we do see the DCMIP test cases popping up as as evaluation methods, which is super nice. Not every test case might make it, so if the community decides this wasn't good, that's fine, but we will be exploring a very new set of test cases that nobody has done before, and you're the first that can kind of take a look at that, right? All right, this is here my really amazing team here from the University of Michigan, and they all contributed, to the success of DCMIP in various ways. Tim was really the lead. He's sitting here in the front. He will also present later. You will also see the faces here. And Garrett and Owen here in the first row, they were really instrumental also putting test cases together and also helping with the machine learning component. And then Nicholas Androwski, also in the second row, he put together one of the test cases. And then everybody was helping. We did 2 weeks of boot camp in Michigan to test actually whether it's all okay for you, So if there are hiccups, maybe, so be gentle with us, Tell us and we will fix them as we go. Okay, and then we have another group of organizers. So these are now, the folks here from NCAR, from Indiana University, also instrumental mentors. So these are kind of the group of mentors, additional mentors, in addition to the Michigan group. And then we have speakers, So here you see now the group of speakers. Actually, Will is in the room. I saw him. He will actually be giving a talk this morning. So, third talk, I believe, Right. So here's kind of the group of speakers. And here is David Hall from NVIDIA, and here is Dima Korkov from Google. Google DeepMind, and they will be talking tomorrow about these new machine learning exercises, or not exercises, but models, emulators. Greg Hakim, actually, you see him, he's the one that actually put together the ideas behind these idealized test cases for the machine learning element. All right, yeah, you will meet everybody, this is just a heads up. Also put up those faces if you want to get a refresher who everybody is. They're all available on our DCMIP webpage, which we also will click on soon. Okay, yeah, so here's an overview of DCMIP in general. Yeah, see, Peter mentioned we did it in 2008, in 12, in 16, and now here we are 9 years later. Instead of 2020, it's 2025. And we will be looking, as I mentioned, on the impact of topography on the flow field. So every DCMIP had different themes. Back in 2008, we didn't even have access to non-hydrostatic dynamical cores. Yeah, so this was really coming along in 12 and 16 when we invited, the international community. This was even a 2-week event back then. The international community came here. We had 12, 14 different modeling groups here from around the world, bringing their models to NCAR and working with the students on these models. This was very exciting, and I actually have a couple of photos from that. Here you see some of the groups here from 2008, 12, and 16. And here you see kind of the organizing committee from these years. And I think, Peter and I were there from day one. Yeah, you see us. And also Mark Taylor joined us 2008, 12, not in 16, but he's back this year. He's back here. Yeah, so we have a couple of old-timers and, of course, new folks, which is always a great thing. So maybe you know even a few. But if not, Colin Zazicki, you will meet him here actually on Wednesday. All right. Okay, and this is a typical afternoon, yeah? So here you see these are now photos we took from many years. So this is actually just a portfolio of many, many DCMIPs. Yes? And here you see now a lot of the acronyms are the modeling teams. Maybe you recognize a couple of the IFS, for example, that's the ECMWF model, or Endgame, a model from the UK Met Office. And actually, I'm very excited to have, where's Tom Bendel here. Oh, in the back. We do have actually, not that we asked Tom to run the DCMIP test cases this year, but he's here and he will also present on the latest and greatest efforts at the UK Met Office and also will play with the test cases himself. Maybe Tom even had a chance to play with some. Okay, he's nodding. All right, we maybe see some. All right, but every 3. So you see actually models here. We had also, back here a few years ago, for example, FE3, which is a model we feature again. This is a finite volume dynamical core from GFDL, a NOR model. And then we have MPAS featured, which is kind of up here in the corner. And we have the spectral element dynamical core where, it's actually hidden here under ACME, the acronym. Oh, do we have? Oh, ChemSE, right. ACME is also actually spectral element dynamical core from the DOE version. Back then was called ACME, now it's E3SM. And then we have the NCAR version actually here, the ChemSE version, right? Okay. And yes, and we published this book. It was a lot of work actually, but well worth it. I think it's used still, I think, as a resource for many, even researchers, I think. All right, and this is you, yeah? So this is now the group of about 50 students, and I just put up a map, not really listing numbers. The majority is from the United States, but we have about 12 international participants here, yeah, that came from very far, like New Zealand. Who's that person, actually? Prasan. Okay, so, okay, yeah. Welcome, yeah, New Zealand. That was a long flight for you, yeah. Welcome. No, that's great. Yeah, we have people from China. We have people from Europe, mostly UK, Finland, Germany, and Italy, and also folks from Canada. I think three of them. I think even, yeah. And then a good distribution, I guess, across the United States. Okay. All right. Here are this really brief overview of the DCMIP test cases. Let's review. So we are using 3 dynamical cores, and we were, pinning it down to the 3 because these are the ones that are available to us via the NCAR framework. Yeah? NCAR has the so-called community atmosphere model, which is the atmospheric component of the big climate model here at NCAR, which is called the Community Earth System Model, or CESM. And I know some of you have probably experience with that model, but we are now looking only at the community atmosphere model and the dynamical cores. And there are actually more than 3 in that framework. but we were picking the ones that we can also switch over to a non-hydrostatic configuration. And these are the three. This is a DOE, NCAR, spectral element dynamical core. The non-hydrostatic version actually comes from the Department of Energy, and Mark Taylor was heavily involved in that, a lead developer here of the non-hydrostatic version of SE. This dynamical core will be the new default for NCAR once CESM 3 gets released, or CHEM 7, which is up and coming. I don't know the date, but within maybe the next year or so. Yeah, optimistic. Well, we have the other model from NCAR, which is a model for prediction across scales, or MPAS, which is also built at NCAR, but it's actually in M-Cube. M-Cube is the mesoscale meteorology division here, and they mostly look at weather, not at climate. But that model is now available in this climate model as a switch-on option. And then last but not least, we have the model from the NOAA folks, GFDL, or Geophysical Fluid Dynamics Lab, that's called FE3, Finite Volume Dynamical Core on a cube sphere grid. And they have both the NOAA model and also the DOE model. They have switch-on actually flags for hydrostatic versus non-hydrostatic in a name list, so we can even decide. The MPAS model is only a non-hydrostatic one. Okay, and here you see the laundry list, and these are really just high-level keywords, what the test cases will be about. So we have a dry, they actually go down in scale, and I'm not looking at machine learning right now, but meaning the first one is large scale. It's even hydrostatic from a kind of when you look at the motion. And this is actually a mountain flow that creates inertial gravity waves. And here we are looking at actually the vertical resolution. What's the impact of vertical resolution on the impact of this traveling gravity wave and the breaking of the gravity wave? Number two goes down in scale. We are now shrinking the Earth by a factor of 20. We are not quite non-hydrostatic yet. Yeah, we have 5 kilometer spacing here, number two. And that one is also a mountain-generated flow field, but using two options. Two options means two different mountains, but initial conditions are otherwise identical. And we will do a so-called gap flow where the flow squeezes through a mountain gap. And that's happening in nature, yeah. So it's accelerated as it's squeezed through mountain gaps. And there are all kinds of swirls and things happening, yeah. So that's something up for grabs to analyze. And then we do a vortex shedding one, which is a so-called Van-Karman vortex street. Maybe you have seen this in satellite imagery. Very beautiful, yeah, behind like typically islands with a volcanic mountain, you often see these swirls in the cloud field, yeah, and it's something we were able to replicate here with a dry dynamical core. It's not showing clouds, but it's showing the swirls. And this is called the 2B, the vortex shedding one. And they are smallish. Yeah, these flows are on the order of like 100 kilometers, maybe a couple of 100 kilometers, but they're not thousands of kilometers wide. And then number three, we really shrink it down to an Earth by like a shrink effect of 60. And then we go after 1 or 2 kilometer grid spacings, yeah, in that small world. And then we add physics to it, rain physics, simple rain physics. And this is a squall line test case, actually, with thunderstorm test case. And then number four is independent of that. Yeah, that's investigation of machine learning emulators, pre-trained with ERA5 data, but we are using them out of sample. Yeah, so these are GraphCast and spherical forecast net, which we are using via a portal from NVIDIA called Earth-to-MIP. And here we are giving it kind of fake initial conditions, and we are doing forecasts and see whether the emulators can grab the flow field. Yeah, so it's a little bit out of sample. We will see what we are learning. Yeah, so you probably have even, yeah, if you have more ideas, this is really very exploratory. Okay, and I should really note that this wouldn't have happened without the sponsors. And the main funding is from the National Science Foundation, the NSF, which funds a lot of you, not everybody. Some of you were self-funded, or some of you live in Boulder. But NSF was providing a majority of the funding. We are supported here, greatly supported by NCAR. And this means we have, even here in this room, we have media support here. I kind of list the two divisions that are involved. This is CGD, Climate Global Dynamics Division, and CISL, which is a computational division. CISL is helping tremendously with the compute environment, and that actually presents somewhat of a challenge because the machine is down this week. Yeah, the mainframe, it's called the ratio, has a down time, and this was a very big hurdle for us, but I think we have a solution and we are hoping the solution will hold up. But I'm not guaranteeing that we have access to the machine at any given time of the day. The machine might be offline for short periods, I hope, if it's getting, if needed. But you will hear more about that. But we do have machine compute resources here, and this was really done and supported by the CESL group that you see here. And on the Michigan side, I had help here with great, and you probably were in contact with Sandra Pretlinski, those got funded, and I have other admins that were involved. Alrighty. Okay, a typical day, and I should wrap up. This is a typical day, yeah. So really easygoing, very informal, and you also feel free to ask questions as much as you want. Yeah. So we have long lectures. The first one typically is short, half an hour, but you see we have typically hour-long lecture slots, and speakers are advised to maybe talk for 45 minutes, and definitely time for questions, like 15 minutes or so, yeah, to interact. If they're burning questions, I think they will entertain other questions as well. Then we have lunch in the cafeteria here at the Mesa Lab, which is self-paid. It's about $10 or so, depending what you pick. Yeah, you have choices there. And then we go over in the afternoon to the library and have hands-on sessions with a break in between, which is getting refreshments, and so are catered here. And typically 5:30, except Friday, we have the bus pickup at 5:30, gets you back to the hotel. I don't think I have time to click on the schedule. We do this later, and feel free also to check that out. Maybe before we stop, logistics. DCMIP is a very interactive event, and we will be using the wiki as our communication platform. And you have the link here, and I hope everybody has access now, edit access. I know there were some hiccups yesterday with the Google accounts that I didn't know, but I hope if you don't have access, let me know. I add you and provide you, please, with your Google account information. Yeah. This wiki, this is a Google site, will also be used for your results or the interaction among your groups. Yeah. So this is the hands-on portion is also using this as a platform for communication. Yeah. We will be creating many extra pages. Yeah. Don't delete anybody else's, yeah. So that is technically allowed, yeah, but you don't want to do that. All right. Okay, we provide a little bit more information in the later afternoon and then morning. And last but not least, computer environment. If you have trouble connecting to the system, we would like to know, because we do have people here from CESL that can help with that. Yeah. So I don't know. Can I see hands up if you had trouble? 2, 3. 3 people. All right. We want to maybe hook you up with some admins, yeah, to clarify what the problem is. And then we are using the machine called Casper, which wouldn't be our normal choice. Yeah, this is typically a data analysis server. And we have a reservation, which is very generous. We have 4,000 CPUs, 24/7. So it means that you can use them at night if you want. Yeah. I just want to say, it sounds like a lot, but actually when you divide it by 60, it's maybe not a lot. Yeah. So therefore, I would like, just as a word of caution, please be gentle in the afternoons with your jobs, meaning don't do the high resolution that takes an hour or 2. Yeah. Do just the smaller jobs that finish in 5 minutes. You get results, you have things to analyze, and submit these large jobs at 5 or 5:15 or tonight or whenever, during tomorrow morning from the hotel, wherever. Because they should then be finished and you have them ready as you come here tomorrow. Yeah. So this would be the strategy, to not overload the machine right now in the afternoons. Everybody has a chance to run things, and then later tonight you feel free to submit, and they will then be worked on tonight. Yeah. Okay. I did the group assignment this morning. This was kind of last minute, but it's up. I don't show it. I'm run out of time here. But you want to check it out. Yeah, I posted it here. It's color-coded, and it's also the group is mentioned. So we assigned you all to groups. There are 2 MPAS groups, 2 FE3 groups, 2 spectral element groups, and 1 machine. Well, actually, machine learning, I only listed 1 group, but technically it's 2. There are 8 people in the machine learning group, about 12 or 13-ish in the other groups. Yeah, so this is kind of, and you want to just find yourself, and we, again, go over the logistics a little bit. You see the names here of your mentors also here. All right, and that's it, and that's perfect timing. Maybe if there's a quick question that I could entertain right now. Let me see. All right. Again, we will talk about the DCMIP test cases at 11:30. And then I would, where's that? I think you're next. No? Oh, yeah. Right, so Adam is an NCAR scientist here, actually a University of Michigan alum. Yeah, he's a University of Michigan alum from back in the days. And yeah, he's embedded here in the global and climate and global dynamics division. And I asked him, or we asked him to provide a basic overview of, what's the GCM all about. This is really an intro lecture into modeling. I haven't seen it yet, so I bet he will tell us a little bit about the NCAR framework, of course, not just the generic thoughts. And yeah, he sets the stage. Yeah, and then we stop in an hour. We stop for coffee and snacks.
It's no problem. And where's this thing at? Yeah, so I am the pointer options. I'm looking for the laser. Maybe that's it. Laser pointer. Yeah, Adam Harrington. I'm a project scientist at Atmospheric Modeling and Predictability section of Climate and Global Dynamics Lab here. I'm gonna give a talk called Overview of General Circulation Modeling. We're gonna focus on scales and Introduction to Dynamical Cores. I was a DCMIP participant at the last DCMIP, so 9 years ago. And I loved it, and it got me in touch with NCAR. That was sort of my introduction to NCAR. And I'll say the one reason I really liked DCMIP is when I was a graduate student, I was very overwhelmed by GCMs. I can press play and I can run them, but I had no idea how they worked. And they're so extremely complex that most people who run GCMs don't know how they work. And so it's really kind of nice to have these idealized test cases with really simple physics or no physics, simple topography. These are things that you can wrap your head around. You can actually wrap your head around the different components of the model in these idealized test cases. And you do feel a little more in control. And so I'll just say that I think that's a nice way to teach people how GCMs works, is to start with these DCMIP type test cases and then work up from there. I'll say, 9 years later, I still think GCMs are enormously complex, and I still don't have a handle on exactly how everything works. But I'm learning new things every week now that I work on it for a living. Okay, so full disclosure, I adapt a lot of these slides from Peter Lauritsen's CSM tutorial talk on atmospheric dynamics. And that includes this figure here of all these grids. I just want to point out this grid over here. This is called the yin-yang grid. It's just kind of a unique grid. We don't use it here at NCAR, but it's kind of like you have the surface area of the sphere is these two sort of canvas patches like a baseball that get stitched together at the seams. So just wanted to acknowledge the uniqueness of that grid. So for GCM modeling, we use GCMs to model planetary atmospheres. And so the domain is a sphere, a planetary, it's a spherical domain. The planet that we're here focusing on is Earth. The Earth is rotating. and it has a lot of complex structures, as seen from the snapshot from space of the cloud field. And so the first thing you do is you tile up your domain into non-overlapping grid cells. And this defines the size of these grid cells defines the resolution of your computational grid. That's not the same as what we'll call the effective resolution, which is the actual resolution of the model. So more on that in a little bit, but keep in mind that the computational grid is not necessarily the resolution of your model. But we use the computational grid to solve the governing fluid and thermodynamic equations on the resolved scales. And so this is the dynamical core's job. So the dynamical core, while it's solved on this computational grid, in almost all cases, the solutions at the grid scale, so 2 delta x, are not accurate. And so within the dynamical core, there are filters. These may be implicit filters associated with the numerical method. So if you have a very diffusive numerical method, that's an implicit filtering. Or if you don't have a very diffusive numerical method, you might have explicit numerical filters, such as hyperviscosity operators. And these are intended to remove these inaccurate scale features that the dynamical core produces. So in the end of the day, the dynamical core is trying to provide a reasonable solution at the resolve scales. And since that includes this filtering, the resolve scales does not include 2dx type modes. In modeling jargon, we refer to the dynamical core as the DI-core, or the dynamics for short. So that's what we'll be using probably throughout the next 2 weeks to refer to the DI-core. Physical parameterizations. So many important processes occur at the subgrid scale, and they need to be parameterized. That's pretty apparent from this comically coarse grid, where you have a lot of fine scale structures at the subgrid scale. And so these parameterizations compute the grid cell average tendencies due to these unresolved subgrid scale processes. And it does it as a function of the grid cell mean state. So it's an extremely difficult problem. You have to take the average of the state over this grid cell and use that to approximate the impact of these subgrid scale features on the resolved state. So you have to, well, I'll put it this way, that the DI-core solutions are much more accurate than the physics solutions, because it's such an impossible job to sort of parameterize the effect of things you aren't resolving. In modeling jargon, we refer to parameterizations as just the physics. And so you have the physics and the dynamics that really make up your GCM. Sometimes we refer to the physics as just column physics, and that really emphasizes a property of physics, which is that they're very local. They only consider or operate on the state in a grid column. So the physics doesn't incorporate information from neighboring grid columns in order to inform what it's doing at this grid column. Nor does it provide tendencies to neighboring grid columns. It's all extremely local. There are exceptions of schemes that do use neighboring information, but they're much more the exception rather than the rule. Okay, so we've got these two big components, physics and the dynamics, and we couple them together to basically make our GCM. And so here's sort of a high-level workflow for how these two pieces of the model couple to each other. So, oh yeah, here's where Excel's screwed up a little bit. This is supposed to say 1, 2, and 3. So this is supposed to be a list in order. And so step one is you you have a state that you use to compute the total tendency from the temperature, humidity, the winds and tracers from the physics suite. If this is the first time step, that state is usually in the initial conditions. If this is sometime within the model run, that state is coming from the die core. This physics suite is what we call, basically it contains multiple physics schemes that we represent all the processes that we need to parameterize. These physics schemes may be coupled to one another or not coupled at all. And what I mean by that is that essentially you have a bunch of different physics processes and schemes, and they can, what we do in CAM is we use this sequential update method for coupling the physics to one another. So we sort of invent this this sort of virtual physics state that evolves as you progress through the different physics schemes, whereby each physics scheme will update this sort of virtual physics state with its tendency to feed that state into the next physics scheme, which will then provide a tendency, and you'll update the state again. And so you have this sort of virtual physics state that's evolving through the physics time loop. But the only thing we're sending to the dynamical core is the sum of the tendencies. And so the point of this sort of evolving physics state is just to provide more accurate tendencies from the physics schemes. So it's not really a real state in the model, because we'll take the sum of those tendencies and then we'll basically integrate it with the dynamical core using that original state in one. And so this sort of process that I'm outlining you will be discussed a little more in detail on Thursday at 11 a.m. by Peter. But just giving you a flavor that there's different ways you can couple the physics to each other or not in order to provide a more accurate tendency to drive the dynamics with. And so these physics tendencies are then basically a forcing term in the discretized die core equations, and we integrate them forward in time in the die core. So that step is schematically outlined here. This is the time loop and the spectral element die core in CAM. And there's several different processes in the die core that are subcycled within each other. And so there's a lot of subcycling within sort of this host model time step in order to get you a realistic die core solution. So just walking you through this example, at the top of the loop, you apply your physics tendencies, and then we start going into another nested loop. Here we're advancing the 2D dynamics, and then we're nesting into another loop where we're applying these filters that I was talking about that remove inaccurate modes. You then exit all these loops, and then this is the last step. This is the vertical remapping step. This is where your vertical motion is sort of realized in the Eulerian reference frame for this die core. And so we're basically splitting up different parts of the die core here, where we're doing 2D dynamics here, filtering here, and vertical dynamics, if you will, last. So you then update, you now have a new prognostic state, you increment your time step, and you send that state back to 1. And you repeat it, and you repeat it, and repeat it. And that's the anatomy of a time step in a GCM. There's one thing that I didn't include here is where in this sort of time loop do you couple to the surface components like the land model or the ocean model or over sea ice. That depends on the GCM. In CAM, we actually do it about halfway through the physics phase, which I'll try to outline why we do that in a little bit, but you're free to sort of couple with the surface components in different places in the time loop. Okay, so what's in this physics suite that I talked to? So what type of processes are we trying to represent? So a physics suite would contain radiation. It will have a PBL scheme. So this is mixing due to subgrid scale turbulent fluxes in the boundary layer. The PBL scheme is also where you apply the surface drag in the model. So this is where you feel this is the tendency that tells the model, I'm feeling the surface, I'm feeling the drag, okay? And that gives you that logarithmic profile of winds with height. You also have a PBL form drag scheme, and this is just drag due to unresolved orographic obstacles in the landscape. And then there's a gravity wave drag scheme, which parameterizes basically vertically propagating gravity waves that break aloft and provide drag on the general circulation. This is something that's important for getting your polar night jets looking realistic in course models. And the gravity wave drag can have a variety of sources. It could be subgrid scale orography that's triggering these propagating waves. It could be convection, could be fronts, could be other things. Cumulus convection is very important to parameterize, and that's because convection occurs over a very large range of scales. And for that reason, a lot of times there's separate schemes for shallow convection and deep convection. Sometimes there's even closures for mid-level convection. Yeah, a very important and crucial component of any GCM. The next thing I have listed is a stratiform macrophysics and microphysics. So this is, in essence, the thing that's forming, the macrophysics is the thing that's forming clouds at the grid scale or at the subgrid scale. So it's doing, it's your main cloud formation scheme. The microphysics part is doing sort of finer scale processes such as activating liquid droplets, or in order to provide you the number of cloud droplets that are in this mass of cloud that you formed, auto conversion to rain and snow, or grapple, and also simulating the evolution of those condensates as they fall through the atmosphere and experience things like evaporation or coalescence with other condensates or pieces of cloud. So the microphysics can be very complicated. The macrophysics, it should be noted, it's the thing that performs the saturation adjustment in the model. So it's a thing that keeps relative humidity from going way over 100%. So if somewhere in that grid cell you have supersaturation, the cloud macrophysics is going to condense that moisture to bring relative humidity down to 100% in that place. And this is an instantaneous process in the model, and so therefore it's the fastest process in the model. So historically, for that reason, the state after the saturation adjustment, and this is again in this virtual physics state loop, is what we actually consider the most realistic atmospheric state in the time loop, and it's often that is where it is written out into history files, is the state at that point in the time loop. And so going back to like where do you couple with the surface? So one reason you might want to couple with the surface, that is one reason why you might want to couple with the surface components at that point in the time loop, because it's considered historically to be the most realistic atmospheric state. That's not a rule of law. So that could be investigated, and maybe other places could be found to be more accurate as well. But it's more a convention that we live by. So, the specific choice of the processes that are represented in your physics suite, and specifically what scheme is used to represent that process in your physics suite, is really going to depend on the scope of the model. And so next, we want to talk about what are you designing this GCM for? is this for numerical weather prediction, or is this for climate, which is much longer time scales, and things like mass and energy conservation might be more important in that situation. What type of meteorological processes do you want to resolve? Planetary waves, extratropical storms, or finer convective type structures, squall lines, tropical cyclones, and even supercells. What type of additional complexity do you want to have in your model? Do you want to have a lot of atmospheric chemistry in your model? In which case you have like 200 traces or something like that. Do you want to have a stratosphere? So if you want to resolve a stratosphere, you want to maybe simulate a realistic QBO, then that tells you where your model top needs to be in order to resolve the stratosphere. And in the extreme case, what if you want to simulate space weather? So this is, charged particles interacting with the geomagnetic field, and occurring 500 kilometers above the surface. So these choices really constrain the scales that need to be resolved by the dynamical core. And so this will constrain basically the equation sets you need to use. So if you want to do a realistic job, it's resolving convection, you're going to need a non-hydrostatic dynamical core. If you're interested in space weather dynamics, you might want to have a deep atmosphere approximation as opposed to the shallow atmosphere approximation. So this scope really does limit or help constrain what equation sets you're going to use. And different equation sets have different prognostic variables. Hydrostatic models don't prognosticate the vertical velocity, whereas non-hydrostatic equation sets, of course, do. There's other dynamical core design considerations, such as what's your vertical coordinate? So do you want to use a pressure-based vertical coordinate, or do you want to use a height-based vertical coordinate? What grid type do you want to use? Do you want to use a yin-yang grid? Do you want to use a cube-sphere grid? And then what's your discretization method, the numerical scheme you want to use? Finite volume, finite differences, spectral. And the order of accuracy of your scheme, so how important is order of accuracy? And then the arrangement of the variables on the cell, so how the different variables are staggered on the cell. For example, this is the finite volume model where you have staggerings of, V is face-centered, perpendicular to the face, whereas U is parallel to the face here on this top one. So there's a lot of degrees of freedom on the different arrangement of variables, and therefore there's all these different names for the different arrangement of variables, like the C grid and the CD grid and stuff like that. Not going to be any equations in this talk, so but I think you'll learn a lot more about staggering of variables and some of the more in-detail lectures on dicores later this week. Another consideration is mass and energy conservation. Like I alluded to, for weather short-term prediction, you might not be so interested in conserving mass and energy, whereas over climate scales, you certainly probably don't want to be leaking energy out of your system. And so mass and energy conservation might be very important for you. And another consideration is tracer transport properties. So in the example of chemistry where you have 200 tracers and many chemical reactions, you want to try to represent that as accurately as possible. And so you want to consider things like monotonicity or shape preservation, whether this thing preserves linear correlations between two reactive species. But one I think that's really important is scalability. So how much additional cost is it to add another tracer? So if you have a lot of tracers, you want this thing to be either super scalable or linear scalability. You don't want to have some situation where it's becoming increasingly more expensive to add an additional tracer. Okay, so I'm going to dive now into scales. So circling back to this effective resolution idea, which is the smallest scale that a model can accurately represent. You can define it in terms of a horizontal wave number, we'll call KF. This KF can be assessed analytically using for linearized equations. But in a full model, you can assess KF looking at the kinetic energy spectrum of a particular prognostic variable. So an example of that is this schematic from a book chapter written by Bill Skamrock. The energy density is on the y-axis, and on the x-axis we have our horizontal wave number. The solid line is the model's spectrum, and the thinner line is the correct spectrum, which we would derive from observations. So over at this horizontal scale, this is the 2dx wavelengths. You'll notice that there's a lot less power at this scale, and that's the numerical filters in action. So they are removing all of these scales that they can't accurately represent and want to toss in the trash. They're very scale selective, and so it will just try to target sort of this tail end of the spectrum. And so it's where your model spectrum departs from the observed spectrum is what you could use to quantify the effective resolution of your model. So the answer is that it ends up being anywhere from 4 to 10 times the model grid spacing. That's the smallest feature that you can represent in your model. So let me give you a real model example. This is a sequence of aquaplanet simulations I performed at different resolutions, starting from 2 degree or so here in blue, all the way down to 1/4 degree, or it's about a 28 kilometer grid spacing in black. And so this is the kinetic energy spectrum of the zonal winds at about 200 hectopascals. And you can see that this fall off in energy down here is showing the filters in action. In order to make it a little easier to see where that fall off is occurring, here's sort of a scaled version of the kinetic energy spectrum in which a horizontal line here is equivalent to a slope of -5/3 in the raw spectrum, which is roughly a slope around here. So if you look at the 28 kilometer solution, you can see that it really starts falling off at about order 100 kilometer wavelength. So, that's very much consistent with this idea that the effective resolution is 4 to 10 times the grid spacing. This thing's lining up with about 200 kilometers in the center, so that's, about 8 dx or so. Okay, so that's how you would identify the scales resolved in the model. Let's now sort of step back to do some more atmospheric 101 and just really try to delineate the different atmospheric phenomena and the scales that they occur at in the real atmosphere. The atmosphere is a multi-scale phenomena in general. And we'll start with first I'll introduce this schematic here from a book chapter written by John Thuburn. This is this book that we were just plugging. So it born out of I'll call it the prequel to DCMIP. And so you've seen figures like this before, where you have time scale on the y-axis and horizontal scale on the x-axis, and just sort of denote features that are associated with those scales. So at the largest scales, we have 10,000 kilometer or planetary scale, basically. Like, what's the radius of the Earth? It's about 40,000 kilometers. So these order 10,000 kilometer circulations are things like the Hadley circulations, planetary waves, which are just sort of undulations in the jet streams or pressure patterns associated with these larger scale Rossby waves. A little finer than that, you have order 1,000 kilometers. You have your cyclones and your anticyclones, our day-to-day synoptic weather. And a little finer than that, we have fronts. So on order 10 kilometers, you have these boundaries between warm and cold air masses that are kind of dynamically interacting over a very narrow width of a few tens of kilometers. And then going a little further down this dashed line here, we're getting into convection. And as I alluded to earlier, convection occurs at a very large range of scales. These can be very large scales, such as tropical interseasonal oscillations like the MJO, which occur over 1,000 kilometer scales. Squall lines and supercell complexes and tropical cyclones would be more at kilometer scale. And then you can, and then in the small limit, you have these sort of individual small cumulus clouds sitting atop the boundary layer. So all of these features that lie on this dotted line here are very important for weather and climate, and they need to be represented in numerical models, whether they're parameterized or they're resolved. There's no spectral gap either. This is a continuous amount of energy across these scales, and there's even interaction of smaller scales with large scales. That those interactions need to be represented as well. We can be dealing with cascades downscale or cascades upscale. And maybe it's obvious, but because there's no actual spectral gap in the actual atmosphere, it makes it very difficult to model weather and climate. Effectively, you can resolve down to your effective resolution, and then you need to design your physics parameterizations to pick up and represent that scales all the way from the effective resolution all the way down to the molecular scale. And so it's hard to do that seamlessly because we split up. We do have a spectral gap in our GCMs between the effective resolution and the parameterizations. And it's up to the parameterizations to just try to make that as seamless as possible. And it's a very challenging task. I want to point out these dotted curves down here. So these are dispersion relationships for inertial gravity waves here and acoustic waves down here. Relatively speaking, they're energetically weak compared to these more dominant processes. Certainly when it comes to acoustic waves, we do very little damage or no damage if we distort their propagation. But the fact that these waves are fast really makes it challenging for the dynamical core because if they're using an explicit time stepping method, the speed of these waves are controlling, puts constraints on the size of your time step through CFL limiting constraints. So now I want to focus on the gray box here. So this encompasses the range of scales that are represented in typical present day climate models, which you all know are 1 degree or so 100 kilometers, and their effective resolution is larger than that. So you're not resolving any of these processes outside of the box, and those need to be parameterized. So we developed CAM at 1 degree resolution, but we have been able to run it down recently to about 3 kilometer resolution using MPAS. And so I added this red line here showing approximately where that domain would be. And so this is dipping, once you go down to 3 kilometers, you're dipping down into the point where you're actually resolving acoustic waves because your time step needs to be on the order of 10 seconds or so. And so MPAS being fully compressible is actually resolving these internal acoustic waves. And it's resolving some aspects of convection. And so once you go to higher resolution, there may be parameterizations at 1 degree that you don't need at 3 kilometers. There may be parameterizations at 1 degree that's approximations break down at 3 kilometers and they need to be reformulated. So to give you sort of a real model example of this, let's just posit the question, do we still need to parameterize cumulus convection at 3 kilometer grid spacing? Well, the answer is yes, I already told you. It's not resolving all of the cumulus convection. And so, but what does this look like in practice? And you know, it's a little more murky. So on the left panel is just a snapshot of the cloud field in this 3 kilometer model. I've turned off the deep convection scheme. The only thing that's on is the shallow convection scheme, which may or may not be doing a good job at shallow convection. And what you get is these sprinkles of deep convection everywhere. And it's not really realistic. And what's happening here is that at 3 kilometer grid spacing, you're resolving these, you're permitting these like 10 kilometer or so updrafts, right? And there are 10 kilometer updrafts in nature. The problem with these 10 kilometer updrafts is that the eddies that are responsible for lateral entrainment and mixing with the environment, of the plume with the environment, are not resolved. And so you end up with these updrafts that are pretty much undilute. They don't mix with the environment, and so they're very buoyant, and so their level of neutral buoyancy is 10 kilometers, you know. So these models can only support a very deep mode of convection, and so it can represent that process fairly well, but transitional regimes between them, going from shallow to mid-level congestus to maybe a less deeper convection to a deeper convection, that's not going to be realized. And so the model only knows this deep mode, and so it just represents everything in this deep mode. On the right side, I added some parameterized mass flux plumes to the model that will handle anything from shallow, mid, to deep convection. And as you can see, you start getting more realistic spectrum of clouds. You're not getting these sprinkles of deep convection everywhere. You're preventing the dynamics from having to do this all the time. So that's what that kind of looks like in practice when you go to higher resolutions. Okay. Now I want to spend some time talking about all the die cores in CAM. So there are several of them. Here are 7 or 6. Except that earlier this year, we had decommissioned the Eulerian spectral transform die core. We're sad to see it go. It's one of the first die cores in the model, and you know, developed by David Williamson and others. The reality is that over time, we just add more and more stuff to our code. Okay, we add more die cores, we add more physics, and it gets to a place where the code is becoming somewhat unmanageable and some things just gotta go. So we figured it was time to ditch the Eulerian die core in order to make it easier for us to maintain this code. We have the finite volume die core, which operates on a latitude-longitude grid. That one might be on its way out next, so just a FYI there. FE cubed, which is just a cube sphere version of that, is available. Then we have the spectral element die core with CSLAM advection. This CSLAM stands for conservative semi-Lagrangian advection method, I believe. And the newest die core is this non-hydrostatic spectral element die core from DOE that Christiana and her team are implementing currently into CAM. It's not officially in CAM yet, and so it sits on a branch that will eventually be merged in. I suspect that's the branch we're all going to be running this week because we're running the SE non-hydrostatic die core. And then we have MPAS, which came in a few years ago. So of these, there's only 3 that are that support non-hydrostatic equation sets, and that's FV cubed, SE non-hydrostatic, and MPass. When you the scale at which you conventionally need to use a non-hydrostatic dynamical core is based on the scale analysis of dispersion relationships, and it's based on the limit of the horizontal wave number approaching the vertical wave number. And so what's the largest vertical wave number in the atmosphere? Roughly the depth of the troposphere. And so it's when K reaches about a 10-kilometer wavelength that these dispersion relationships indicate that you need to use non-hydrostatic dynamics are important, and that you can no longer use the hydrostatic approximation, that there are non-hydrostatic pressure gradients that are important. So the rule of thumb is for length scales 10 kilometer and smaller, you need a non-hydrostatic dicore. There are studies out there that show when I turn on the non-hydrostatic switch at even 25 kilometer grid spacing, I see a big difference in the solution, and that indicates maybe non-hydrostatic dynamics is important at even coarser scales. And think about what that means. At 25 kilometers, we already showed your effective resolution is order of 100 kilometers. So the actual scales you're resolving are still order 100 kilometers, and those studies are indicating non-hydrostatic dynamics may be important at those scales. So that means that this could be either way off or not, but that is the conventional wisdom until someone figures out what the true answer is. We support mesh refinement in SE, both of the spectral element dicores in CAM, MPass, and FE cubed as well. This is an MPass mesh refinement, and all the rest of these are SE. So we've been running SE mesh refinement for a long time now, and so we have a lot of examples which are shown here in different areas. And obviously this is really ideal because you can start to simulate higher resolution features without the overhead of simulating it globally everywhere. And so this is a more computationally practical way to study higher resolution. So the individual dicores that we're running, there are 30-minute talks that'll go over details of the implementation of those dicores. So for the SE non-hydrostatic, there's a talk on Thursday at 8:30 a.m. with Mark Taylor. And I'll just go over high-level points of these dicores here just to give you something to chew on in the meantime. SE is based on HOME, this higher order method modeling environment from over 20 years ago. And so the first version was a hydrostatic version of SE. It's basically the way it's discretized is you have a cube sphere and you tile it with quadrilateral elements. So these are elements, and this is a finite element-based approach, meaning there's structure of the solution within the element. And that's represented with a 4th order basis set in each horizontal dimension in the element. And for 4th order basis sets, that means you basically have 16 nodes or grid points within each element. But they share some of them, the boundaries are sharing nodes. And so each node, each element has 9 independent grid points, if you will say. So if you want to think of resolution, the computational grid, you take an element and you would divide it up into 9 grid cells or whatever. And that's the resolution of the computational grid for the CAM-SE. It was reformulated with a non-hydrostatic equation set, and then an efficient semi-Lagrangian tracer transport scheme was implemented. And the physical parameterizations are actually not evaluated on this basis set representation of the state, and we actually integrate these basis sets over finite volume cubes within the element, and so that the physics is actually being evaluated on the separate finite volume representation of the state. It also has really good mass conservation and energy conservation properties. FV cubed, Christiane is going to talk about that at the talk after Mark, Thursday at 9 a.m. It's a cube sphere version of the finite volume die-core. Uses a flux form semi-Lagrangian advection grid on it. It's like a staggered CD grid, so it's a bit unusual. Yeah, so I don't have much more on that model. MPAS, there'll be a talk from Dave Randall from CU. He'll come down here from CU, and that's going to be Wednesday at 9:30 a.m. It's basically, its grid looks like this. So these are centroidal Voronoi tessellations of the sphere. I just call them hexagons. I don't know what you guys call them. But they're non-overlapping hexagons. There's a couple, oh, okay, all right, well. Hexagon with the pentagons. So it's a finite volume discretization on a staggered C grid. Fully compressible non-hydrostatic discretization, similar to the weather research and forecast model WRF, which I'm sure many of you are familiar with. This is the this die-core uses a height-based terrain following vertical coordinate. So that's different from SE and FV cube that use a hybrid pressure terrain following coordinate. And CAM's physics is based on a pressure-based vertical coordinate. So when we integrated this die-core into CAM, we had to come up with some physics dynamics coupling algorithms that basically goes from height-based coordinates to pressure-based coordinates. And so there's a lot of nuance there in how we implemented that into CAM. So I'm going to go for a few more minutes, and then we'll take questions, I think. So I'll just talk for a second about the pressure-based vertical coordinates that's common to SE and FV cubed. So it's a hybrid coordinate, and it's a hybrid between a sigma coordinate, which is based on the surface pressure. So it's terrain following because your layer is defined by the constant surface pressure. And it's a hybrid with pure pressure coordinates. And so aloft at higher parts of the domain, you transition to a pure pressure coordinate above. And so this hybrid coordinate, you can express just in terms of a surface pressure and a reference pressure that defines the pure pressure, levels. And so yeah, the 3D pressure field is reconstructed by the pure pressure component of the coordinate, and so that's this reference pressure times these A coefficients. So these A coefficients would be close to 0 near the surface, but closer to 1 up at the top of the model. And you added with that is the terrain following component of the coordinate, which is the coefficients would be closer to 1 near the surface, and they transition to 0 at the top. So since there's 0 at the top of the model is a constant pressure lid. And also, the way that we index, the convention for indexing is the index 1 is the model top, and K-lev is the surface, and so your indices are monotonic with the pressure being monotonic. Your pressure is increasing downwards. Another thing that's common to SE and FV is that they use this vertically Lagrangian floating coordinate to do the vertical dynamics in the die-core. So I alluded to this a little bit when I was walking you through a SE die-core time loop, but effectively you solve the 2D dynamics in these layers that can deform vertically, but since you're in a Lagrangian reference frame, it still thinks it's 2D dynamics. Yeah, I'll just jump ahead to say that, you would sort of initialize the state on these undeformed eta surfaces. So eta is the hybrid sigma pressure vertical coordinate, this little eta here. And so you advance it a few time steps, and these layers would deform. And so your vertical motion you can see in a Eulerian reference frame. But in the Lagrangian reference frame, they have no idea that they've been vertically displaced. And so then after these are significantly deformed, what you do is you remap the state back to this reference eta coordinate in the black lines. And that's where your vertical motion is sort of realized in the Eulerian reference frame. So you can see it in your output. So this is just kind of a nice algorithm because you can kind of make a 3D model by just having a bunch of 2D shallow model layers, dynamics, and then your vertical motion is just realized from a remapping step from your floating Lagrangian layers back to your Eulerian reference coordinate. And this is the last slide, just to finish out thinking about the vertical. So I want to talk about the top of the model. So I think all of the grids we're working with here at DCMIP will have a model top at about 42 kilometers. Again, it's 2 hectopascals. That's for SE and FV. It's set by this 2 hectopascal because it's a constant pressure top. In CAM, we have different flavors. We have Wacom tops, which goes up to 140 kilometers, and so you're actually in here in the thermosphere, and you're fully resolving the mesosphere, stratosphere, and troposphere. And these space weather folks, we have Wacom X, which goes up to 600 kilometers, which is up in the exosphere. In CAM 7, which is, we're going to release that officially within a year, hopefully. We introduced a mid-top version that goes to 80 kilometers. So 40 kilometers is down here, right? So you're within the stratosphere domain. You're not actually resolving much of the stratosphere dynamics with these 40 kilometer tops. But the 80 kilometer tops, we are resolving the entire stratosphere. And that's clear because we also, what I didn't tell you is the top few layers of the model, we call the viscous sponge layer. And we just add a bunch of dissipation to these upper layers in the model. This is not, in reality, there is no sponge layer, but this is just a practical requirement in order to keep waves that are incoming from bouncing off the model top and reflecting back into the domain. And so this is just a garbage disposal. It just removes these things, and it's just a practical way to model the atmosphere with a finite top. And so for that reason, a 40 kilometer top in the stratosphere is definitely not resolving the stratosphere because once you get below the sponge layer, you're probably closer to 30 kilometers, 25 kilometers. Okay, so that is the end of my talk, and so I'll take any questions you guys have.
Are we using the mic in the ceiling? Or, yeah, okay, go ahead.
Right, you mentioned that the MPAS die-core was fully compressible on hydrostatic. Are SE and FE3, are those incompressible or compressible, or?
I don't know, Mark?
They're all fully compressible.
Yeah. I know there's, obviously you can use the inelastic approximation to filter out acoustic waves, and so those aren't being used.
So you had mentioned being able to use the energy spectrum for horizontal wind velocity to calculate your effective resolution. Does that vary with altitude, your effective resolution?
I don't think it really does vary with altitude much. Bill Skamrick has a paper looking at it at various different levels, and I think he came to a similar conclusion for the effective resolution.
Okay, Mark?
Thank you.
I was going to, more on effective resolution, I liked your presentation of that, and I think it's a useful concept. I think it's not like, well, there's not a precise definition of it, so it's very hard to compare across, results that people give in the literature. I was wondering what you thought about making that more concrete.
Well, I mean, you could augment your kinetic and energy spectrum analysis with snapshots of individual features down to the grid scale, so you can actually see how many grid cells are representing these features. So I guess just a little more get dirty in the weeds and provide an actual snapshot of the model might be a way to sort of help clarify differences between models in that regard.
And if I can add to that, I computed energy spectra for different versions of CAM, so CAM 4, 5, and 6. And with every version of CAM, the tail was lowered. So the same die-core, but so the physics also affects the spectrum. So you should definitely run the same physics package if you want to do apples to apples. I think, Dama, you have your hand up?
Yeah, I'm guessing the stacked shallow water gives you better computational performance. That's one reason why we do it, right?
Yeah, I think that makes sense to me. I hadn't thought about it.
And then, so how does that compare to like, if you're fully resolving vertical advection and everything?
Good question. Maybe.
Well, just because it's stacked shallow water equation doesn't mean we're not rigorously treating the vertical aspect, because we're following floating Lagrangian surfaces that follow the flow. That's analytically a correct thing to do. And then you map back. And the difference with the 3D models is you just need 3D advection operators, which in general is more expensive.
But don't you lose like something in the vertical interpolation back to the model levels?
There are different thoughts about that, but
Cool.
So yeah, instead of the vertical advection operator having diffusion in the vertical, here it's all in one step in the vertical mapping. There's definitely some discussion in the literature that when you reach non-hydrostatic scales, some groups believe that the vertical remapping is not a great idea. Like from first principles, they're both approximating a continuous system. Owen, I don't know who was first. But Owen, go ahead.
Yeah, this is sort of an open question to people related to what Mark was talking about earlier. Like, there might be a test case that allows one to quantify effective resolution, or at least to do that. You'd have to be careful for it to be model agnostic, to not bias particular grids over others. So, if there are people here who that seems interesting to you, I would be very interested if you have thoughts on how to do that.
And even your mapping, usually people map to a lat long grid to compute these energy spectra. Even how you do that affects the energy spectra.
Yeah.
You had a question?
Oh yeah, so what's the rationale behind decommissioning Eulerian versus FV? What's the reason for that progression?
Yeah, there's a smaller user base community, and it happens to be older. That's the main reason. It's really efficient at small processor counts, and so I think some university users who use smaller clusters are probably not so excited about not being able to use that any longer.
It might be a bit of a silly question. You showed your eta surfaces that they just get distorted up at later time steps. And it makes sense that the top is like a boundary condition that you impose, but the surface pressure also remains the same. So how does the horizontal variability in surface pressure come in?
I don't know the answer to that. Maybe Peter, you do?
I didn't quite get your question.
So is the surface pressure a boundary condition? And if it's constant, but the surface pressure can vary from one horizontal point to another, but it seemed at least from the figure, that it just remains constant at every time.
Well, the surface pressure evolves. When you design your coordinate system, so that the lower boundary is always following the surface. So the surface pressure is basically your coordinate. So that means you don't have any flux through it. Whereas if you have a z-base, like constant height surfaces, if there's a mountain, then you have to deal with, your flow can't go through the mountain, and you have to treat that as like a fully 3D problem. Whereas if you're just following the mass field and there's no flux of mass through that, and there's no flux of momentum through it, so it makes it much easier boundary condition.
Okay, but I assume it changes with time, but is it also different spatially?
Yeah, yeah, it varies in each grid point according to the version type of it. Well, I think I missed you. Go ahead.
Hi, thanks for the talk, Adam. Could you talk about the difference between the deep and shallow atmosphere approximation?
Yeah, I can speak about it in a character level. Basically, it has to do with, we assume the grid cell area is constant with height. And on a sphere, if you're, the boundaries between a grid cell should be triangular like that. And so at very, very high elevations, like 600 kilometers, the approximation of using the same grid cell area at the surface versus, where geomagnetic storms are happening may not be a very good approximation. It might be, I don't know, that is 20% off. And so that's my comically cartoonish answer. Maybe Owen, you can kind of go a little bit through that.
Sure, yeah. So the thing about the deep versus shallow atmosphere is that you've got two approximations that are tied. The shallow atmosphere approximation, you assume that the distance between the center of the Earth and a point in the atmosphere is the same. And that leads to sort of the assuming that you have rectangular as opposed to wedge-shaped columns. But for angular momentum conservation reasons, you tie the shallow atmosphere approximation to the traditional approximation where you discard certain metric terms and parts of the Coriolis force. So if you're looking at space weather, then the variation in the strength of gravity that you discard the shallow approximation and that wedge shape is important for the dynamics up there. But even in the troposphere, the discarding the non-traditional Coriolis terms, those ones that are in the traditional approximation, really impacts particularly equatorial dynamics. Whatever part of the atmosphere you're looking in, there may be advantages to going deep atmosphere. It's a little technical to get there.
Okay, we need to, thank you, Owen. We need to get some coffee here. This is great, this is what we want. Okay, and feel free to ask questions during the talk as well, and most of us will be around here always, so thank you. Alrighty. Usually it takes about 5 minutes to get everybody in, but you're very obedient. You're really fast, so thank you. The bell is very powerful. Maybe I went a little hard there. So as I was rambling earlier on, I totally forgot to I was kind of setting the stage back in 2008. There was so much going on, developing these new fantastic global models that now exist. So like, for example, the MPAS model, SE non-hydrostatic, and so on. But what I didn't mention is, well, there's a lot going on right now that's a little bit different, which is the next talk here, machine learned models, et cetera, et cetera. So I'm very, very excited to have my colleague, Will Chapman here. He's a project scientist in the section. Unfortunately for us, he's gonna move down to CU, but fortunately for us, CU is very close by. So he's gonna start there as a professor, I think in August? August, so alrighty, well, take it away.
Awesome. Well, thanks so much, everyone, for inviting me out to this really exciting conference, or summer school. I was unfortunately in grad school during that COVID period, so I didn't get to take part in a DCMIP, and I'm unbelievably jealous of all you. I had to learn from a book, and it's boring, or more boring. So today, we have a big task. We're going to be talking about just basically setting the stage. You have an awesome suite of folks in the machine learning realm that are going to come and chat with you all, between Greg Hackham, Dima from the Neural GCM team, David Hall, literally some of the experts in climate weather modeling right now using machine learning. So I just encourage you to really take advantage of it, like chat with all these folks. I will be here today. I'm unfortunately going to a conference starting tomorrow, but I'll be around all day if you want to chat. Yeah, so I'm going to introduce myself really, really quickly, and I'm mostly doing this to point out that I spent a lot of my work on forecast post-processing, which is basically taking the output of a model, trying to improve it with some sort of machine learning. I point that out. That was a lot of my PhD, because I'm going to dunk on post-processing a little bit. And I'm part of that community, and it's all in good fun. But my email is here. If you have any questions, you ever want to talk about machine learning or hybrid modeling or super modeling or some of the fun stuff that I work on, I would be really, really happy to chat with any and all of you. So this is what I was tasked to talk about today. So introduce the DCMIP participants to basic machine learning ideas, how machine learning is used in atmospheric sciences and modeling, e.g. for post-processing, hybrid physics machine learning models, full emulators, and for process understanding. Basically, this should be a high-level overview of what we should introduce: various ML techniques, terminology, workflows, applications. This is everything in the field. So we're going to move fast. We're going to move really fast, but I want to give you a good introduction. I want to give you exposure to the space, and then you'll be able to go deeper with some of the other lectures that are coming in. I also want to point out there are some really, really good machine learning graduate students and postdocs in the room. So take advantage of your peers too. Chat with them if you have questions. Let's get going. So quick poll: who in their workflow now or in their research uses some form of machine learning? All right, amazing. That's like 50% of the room. So today we're mostly going to be focusing on what's known as supervised machine learning. That's where a lot of the progress has been. That means when you're mapping some input to a known output that you're trying to get. There is also a whole field of unsupervised learning. We're going to brush that aside for now, and we're just going to be talking about supervised machine learning. So as a first question, does anybody have a working definition that they think of machine learning? Data. Big data, that's one.
All atmospheric calculate, like replacing parts of atmospheric machine learning.
Okay, Owen. Method of statistics. These are all, yeah, so we're seeing some examples, some ideas. This is my bad jargony example of what I think it is. So machine learning is any optimized or optimizable statistical linking function that maps an input space to a desired target or output space. So we have some set of inputs. We want to make it functionally mimic some set of outputs based on the data in the input data, and the input data, and then we can optimize it in some way. And you can disagree with this definition. I think the field doesn't really have a good working definition. So you might notice that linear regression would probably fit right in this. We have a function that optimizes for some fit based on inputs, outputs. Agreed? Cool? OK. So let's go through a big example of something we want to do. Say we have some state of the atmosphere, and we want a machine learning model that learns the next time step. You can replace this with any idea. For a large language model like ChatGPT, this would be the current word you're on, and you want to predict the next word. That's all those models are doing. And we want some function that does that. This will be our machine learning model here. We just want some function that does that mapping. So I can write a function. I'm pretty good at it. I'm just going to have a series of vector matrix operations activated by some nonlinearities with a lot of trainable parameters, and we'll call these parameters this W, this omega symbol. We're all pretty good at vector matrix math. We can do those little translations. And now I just have a bunch of those operations activated by some nonlinearities in the middle here, and it will lead to some output space. So I'm initially going to initialize these parameters with just random weights. I'll sample them from either a Gaussian distribution or some sort of distribution, and I will vectorize the initial state of the atmosphere, push it through these weights. So what will I get on the outside? Well, I will make sure that these weights line up so it looks, the shape of which looks like the next state of the atmosphere. So I'll have some machine learning state of the atmosphere. I have random weights. What is that going to look like? Garbage. You see my slides? No? Yeah, so that's garbage right now. But there is something that we can do with it. We have a example of what we want it to look like, right? So let's develop some loss that we'll call L between those two states. And we'll say, how much do you look like that? So you can use things like RMSE, MAE, any kind of fun functional form that says, this is how good my example looks. So let's take that loss. That can be RMSE, MAE, whatever. Nice. That's our goal. We want to minimize that loss. People say animations are dead. I like them. So we want to minimize that, okay? So make that distance as small as possible. So what do we do? Luckily, this model that we've written, because of a lot of the libraries that have been put out by Facebook and Google and other folks, some of these large machine learning libraries, our matrix operations and nonlinears are differentiable. So we can develop basically the gradient around that loss term. So this is saying, what is the sensitivity of the loss to the parameters that I have? So I can develop that field. Now we have some gradient field. So what do? We now take those parameters in the next sort of sub-time step as we're learning. We're calling this a batch time step, B. And we just take a small step down that gradient field based on this. And if we do that enough times, we showed enough examples, slowly that loss is going to get smaller and smaller. And we're going to have better examples. Showed a lot of data, walk down that gradient field. That's all that's happening in a machine learning algorithm. So I will argue that if you go to a machine learning talk in a strict computer science conference, this becomes less garbage as you move forward. Everything else is just kind of details. All we're trying to do is take this matrix vector operation, optimize it in some way that it looks like the desired state. Are there questions there? Yeah, Owen.
At this point, do you ever use second order information, or is it strictly gradient?
No. So at this point, we are developing, this is like a numerical approximation of these gradient fields that you then sort of walk down. Yeah. The details in the back end, I'm not exactly sure on. Yeah.
There are some gradient descent methods that use second order for stuff. Details.
So were you also updating this ADA or just updating the omega?
So the ADA is what's known as the learning rate. So it's just, there are schedulers that essentially you can think about there is this minimal point in your loss field. And there are times that if your learning rate is too big, you'll just be stepping over that loss. So we have schedulers that can like allow you to jump into those smaller loss fields. There's a lot, you can get whole papers off of updating the learning rate. There's a lot of details in there. So I've condensed a lot of the field information into a very simple schematic. Not trying to be reductive, but we gotta, yeah, this is what our functional understanding is gonna be here. So largely, we have these fields that are kind of interacting with each other. We have some machine learning ideas here that has the definition, and then there's where a lot of progress has been made recently is this deep learning area, talking about artificial neural networks, more basically larger and deeper connections of these vector matrix operations. And these can range from chatbots, linear regression, decision trees, neural networks. You're going to hear a lot of these terms when you start talking about machine learning in general. But broadly, these are fitting into, broadly, this is where a lot of the progress is being made right now in atmospheric sciences. So why are we here talking about this? There has been just an unbelievable boom in the atmospheric and oceanic sciences of machine learning within our field. So you can see this is AMS contributions to the AI conference throughout time. And right around when I was getting into grad school here, there was just an explosion of these methods, largely due to improved hardware, improved software libraries, and the realization that some of the problems in atmospheric science are really well posed for machine learning. So I was going to give you a primer on this stuff, but luckily, Adam did a really good job just previously. So just imagine everything that Adam said in this slide. Now I'm saying it, and I'm doing it very elegantly, right? So we all know now what is going on in a traditional weather climate model. We have a discretization, we have subgrid physics, and there's a lot going on there. So practically, how is this done? Adam also talked about this, so we'll skip over this. We have both dynamics and physics steps kind of interacting, and you're going to hear a lot and learn a lot about this over the next couple of weeks. And this is a figure by Julio Bachmeister kind of showing what the current CAM scheme looks like as we're going through. So we have our dynamic steps going through all of our physics adjustments to the state and then sort of looping through this process. But what I want to highlight here is there are a lot of challenges in operating a physics-based model or a numerics-based model. So as Adam highlighted, they're super computationally expensive. They're really, really complicated. They're difficult to understand. So I think the latest release of CESM has about 4 million lines of code. CAM alone has about 1 million. So there's an unbelievable amount of expertise required to understand the model. And as you heard, Adam's been working on this for 9 years. And there are pieces that you folks understand and pieces that they don't. It takes a whole community to understand fully what's going on. So really, these are only observationally constrained when you hit them with data assimilation. That's not exactly true. We also tune to some observations. Some of our parameterizations have observational fits within them. The physics parameterizations we know contain errors, and it's a really, really hard task to make a physics parameterization. Like Adam was saying, you have to take sort of these mean fields and then interpret everything down to the microscale. And there are numerical approximations within our model, numerical dissipation, all the things that you're going to be learning about over there. So really huge suite of challenges. So why is machine learning well posed to address some of these issues? Well, if you're on the GPU, computationally, machine learning is really, really fast. So right now, the current estimates, we have an emulator of CAM6. We're about 500 times faster than CAM6 carrying the full state variables. Traditional models are really complicated, crazy amount of code. All of the most modern machine learning library suites, the actual model portion is probably 500 or 600 lines of code. That's actually doing the forward pass. These are learning off of the era 5, so I won't call those observations, but it's close to what we have for observations. So they are constrained directly by what we're trying to emulate themselves. And it's sort of handling all of the subgrid, and everything is represented, or imprints of the subgrid is represented on that grid in the era 5 itself. So we're learning directly from those observations. So I would also argue there's some nice nonlinear mappings there that will help with some of the processes, especially on the subgrid. So this is why I think machine learning is sort of well posed. Do people have ideas in their head about why machine learning is not well posed for this problem? Future climate, yeah, we can't train on that. Okay, yeah, there.
It seems like it'd be difficult to attribute processes in a machine learning model to specific physical mechanisms.
Yeah, I will agree with you to some extent. There is some black boxiness about it. The way we're going to have to think about traditional, say, hypothesis testing will be different in the machine learning. So it will take a functionally different form, and I think Greg Hackham will show you some really cool work in which they're starting to explore some of the more physics within the models. So yeah, all of these things are true. I'm not trying to stand here and say that machine learning will solve all of our problems. I think it will introduce a lot of problems. There are a lot of, I think we're going to need to build these things together as a community with traditional models and machine learning models. So in my head, this is a mapping that I've done of 4 areas of machine learning that are currently actively impacting weather and climate. And you can say, hey, there's more than that, and I will be stubborn and disagree with you and just put them into one of those. But you're right, there probably are more. But this is where I functionally map things. So going through these full model replacement. So we're replacing the basically the forward operator in the model with a learned version of that. So we have no strict functional equations in there. Scientific discovery. So we're trying to say, what has the algorithm actually learned about the system? So this is kind of going after your question here. And we can use some XAI or interpretable machine learning to say, this is what we're learning about the Earth system because the neural network has these certain sensitivities within it. So model post-processing, so taking data that has been run through a model, mapping it to some improved state. And this has been going on for a long, long time. So I count downscaling, post-processing, communication, and risk assessment sort of within this framework, and then hybrid modeling. So this is where we're combining our numerical weather prediction models and our general circulation models, maybe replacing some of the subgrid physics with a machine learning-based parameterization, and then running those models sort of holding hands together. So this is how I label these right now. Exciting, exciting, exciting. These have really been going on just in the last few years, old and boring. Post-processing has been going on for a long, long time. And that means that largely it's really rigorous. This is very hard. So I spent a long time with this community and the statisticians in this community, and they're really, really doing a good job. Post-processing models, model output statistics. There's a lot of really good science that's been going on since about the 70s, sort of in this zone. In the other 3 areas, rapid development. The last 5 years has really, really been a fast-moving field. And I think it remains to be seen what will remain from the machine learning space and what will be phased out. But I guarantee some things from this space will still be here. But I think there's a lot of room to understand what the use cases are, what the best practices are. And I'm hoping it's some folks in this room that will help to sort out these details a little bit. So I'm going to go through examples of all of these areas, and we'll briefly chat about what's going on. We'll start with model replacement. And this is probably what's been getting the most attention in recent years. So in this way, we are trying to just evolve or auto-regressively predict the next state of the atmosphere based on the current state of the atmosphere. So here, F, my function, is a large neural network, and the model is rolled out in an auto-regressive framework. X of 0 is the model state at time 0, and then X, or the state at sometime n, is just a mapping that moves through all of those functional time steps. So that's what I mean by full model replacement. Largely, this is happening in the atmosphere component. Recently, folks have been doing this for sea ice, ocean, and land is starting to catch up here. So there's also another paradigm where you can just move from your current time step to some future time step. I think this has been done with some success. And here your time step is kind of defined by whatever your observational interval is. So say you're using ERA 5, the 6-hour product, your time step would be 6 hours. Some folks are going directly from the current state, and say for ENSO prediction going out to seasonal timescales. So also there has been success in that sort of realm. So here is a intentionally inflammatory statement by a machine learning person. Physics-based models are slow, resource-intensive, don't handle subgrid parameterizations well, and thus are poor at representing upscale error growth. They are inaccurate. Machine learning models derive their dynamics from observations and thus can be more accurate, represent weather prediction. This is meant to make everyone in this room angry, so and I think it should be. But this is a lot of the thinking that's going on, especially from the CS side. And I would argue we need to kind of work hand to hand. However, here's some further motivation and a little thought exercise. So electricity costs for 1 year for a forecast system. This is based on experiments on the German supercomputer machine run by Quinting et al. And this is assuming 50 cents per kilowatt hour, a 40-member ensemble that runs twice per day, initialized twice per day, so say 0 and 12, and it runs for a full year. That costs about $44,000 or $440,000, or a nice home in the Italian countryside, or a bad home in Boulder. Does anyone have any ideas about how much it would electricity costs it would take to run the same AI ensemble? Yeah. Hey, folks. Who's giving the lecture here? No, I'll get to that. You'll see. Any ideas?
10 times cheaper.
10 times cheaper. That's good.
The ensemble would be 10 times bigger, right?
You would have a bigger ensemble. You could, yeah. I could, if I scaled it up to that, it would be nuts. So about $200 or 200 euro. A bad bike in Boulder. A good bike other places. And like you were saying, with training, it's about 10,000 euro on top of that. Which I train emulators. I didn't realize I was burning that much money every time I was training it. So it's a little sobering for me. But this is some of the big motivation is that on the GPU, you can really cut down on electricity price for your forward model. There's a lot of big savings there. And
how much does it take to make a reanalysis?
Yes. Yeah, that is a big caveat there is we're learning off data, but that is a sunk cost that's happening once, right? If I want to do this for every year, yeah, so.
How much of that is like just private models?
I will not comment on that. I don't know. Yeah, I know we can speed up our models, but at the same time, a lot of the times when you're speeding up our models, you're making code less accessible. So scientists are hard to interact with. So there's sort of a push and pull in the community. But yeah, we can speed up our models. But this is where they're at now. Owen. Totally. 100%. Yeah. Cool. So NCAR has their own AI weather model. This is WexFormer. Right now, this is our model trained for for weather prediction. It is using the ERA 5. This is a bunch of fields kind of smacked on top of each other. The main development here is happening by myself, John Schreck, DJ Gagne. Dama is in the room. He's working on this also. But you can see we're evolving fields. Functionally, they look pretty good. You'll probably notice that they smooth out as you move through time. And we'll talk about that, and we'll talk about it in the context of effective resolution here in a little bit. So are they good? They're starting to get really, really good. So this is comparisons of the RMSE for specific variables at 500 hectopascals compared to the ECMWF IFS. And what you can see is for RMSE and ACC, largely they're either matching or beating the IFS in these metrics. That's a very big caveat there. I'll also state that ECMWF has invested a big team in making these models really good and deploying their own real-time AI field, and they seem very, very optimistic about whether they are going to be competitive or better than their numerical weather prediction schemes, and it seems like they are. So here's one example of that. This is using the Pangu weather model, and this is just a case study. So this is a forecasted event where they had a really big cold snap over Northern Europe here. There's someone from Finland, right? Yeah. Is that Finland? The red X? Yeah, okay. So, you thought you were gonna get a harder question. So, yeah, so here is the ECMWF ensemble, and here's Pangu weather. They're initializing this, looks like 6 times a day. And the eventual observation was here, this black dot for that point. You can see that Pangu weather locks into a colder forecast about 6 days earlier than their current ECMWF forecasting system. So this is an example where there is a time where the AI model was able to decode the large-scale state probably and drop the model temperatures. So they're using this as a perfect, Finland, yeah. They're using this as an example of one of the success cases that they've seen this. Additionally, you'll see work by Greg Hackham at this. This is a state-of-the-art machine learning model that they've introduced a disturbance in the flow field here, and what they see is that the response is very physical. It looks like an extratropical disturbance. And I think this paper got a lot of attention because essentially it was saying there is some learning of the actual background physics within the model state itself. So Greg will talk more about this kind of stuff, I'm sure. But it is encouraging to see that the response from the machine learning model fits with the physical understanding of what we should see. So some of the big challenges. As of yet, our conservation laws are not respected in the same way. We can constrain some residuals, and a lot of folks are doing that. But model conservation is not to first order respected within the machine learning world. Full state space is not yet modeled for the models, meaning that we're usually carrying less vertical information. We're carrying less actual variables that we're predicting themselves. So when I give you those cost estimates, you also need to take those into account. A lot of times we're seeing problems with long range or long-term stability as we roll them out. There's a huge model smoothing problem, and we'll discuss that here in a second. As you were saying, they're not super well suited for hypothesis testing in the same way that we have traditionally been doing it, meaning I can't shut off like buoyancy forcing and understand how the climate responds to that. We need to figure out different techniques to try to glean model understanding. And there's a major stigma that probably still exists within folks because I think, myself included, physicists and climate physicists like physics. We respect physics. We know physics generalizes. So there's a big pushback against a lot of these things. And I think, again, it's going to be events like this that kind of bridge the communities. So talking about effective resolution, Adam showed some of these plots. So I have kinetic energy. Let's just focus on the top row on the y-axis. And then in blue is the IFS forecast. And then in red and yellow is our Wex-Former model. And what you'll see is we're losing a lot of energy at the high scale. So our effective resolution is a lot less, especially as we move out in time. What I'll state is the burgundy line is a 1-hour time step model. The yellow and red line is a 6-hour time step model. So as you move to higher temporal frequencies, we're able to capture more spatial resolution. This is just due to what's known as a double penalty error in sort of our loss function. So the state of the atmosphere has evolved more in 6 hours. There's more uncertainty of space. So a machine learning algorithm that sees an atmospheric river here, an atmospheric river here, the nicest way to kind of handle that situation is just to smooth out the atmospheric river in terms of minimizing mean squared error. So often we get a lot of smoothing when the time step is longer and longer. So what we're showing here is some improvement there. And there's been a lot of work to try to improve that. Particularly generative AI models are starting to really improve the effective resolution compared to Year 5. So summary. There's been surprising and tremendous progress in AI-based weather models over the past 3-4 years, possibly an unprecedented disruption to the evolution of weather prediction. So AI weather models are here to stay, probably. I think ECMWF is kind of proving that right now. The climate space is still very much a big question mark. There are people working on it, really, really smart people, but we'll see what the actual use case is there. So there's rapid progress, but many open questions remain. Extreme events, and I think we've seen some really good work by NCAR showing large ensemble sides and how they handle those extreme events. Changing climate, forecast uncertainty, there's a lot of big questions here. It's been nice to see that private industry has really taken a hold of some of these things, and there's starting to be a lot of give and take between private industry and the academic community. And some of the weather services are investing strongly, and I think when the weather and services invest strongly, those are the best forecasters. So they are seeing value in this space. So let's move on. Any questions really quickly? Yeah.
One of the examples you had some slides ago showing an animation with a machine learning. I was just kind of curious, for something like that, what are the approximate numbers of tunable or trainable parameters?
Our model has 751 million trainable parameters. But other models are bigger, other models are smaller. So I don't know how many tunable parameters are in CSM. 30, 50, 60, 70? Okay, but not 751 million. Yeah, but this is all, it's optimized, you know, in the back end. So we don't have a gradient. We don't have some sort of tangent linear model or an adjoint for our CSM model, so we can't really determine those sensitivities. Yeah.
So, like for the scientific discovery, does hidden layers can be specifically made in such a way that they can specifically focus on one specific physics?
Yes and no. Let's talk about that when we get to the scientific discovery portion. So hybrid modeling, we're gonna rip through this. So this is where I've actually spent most of my time, is trying to couple machine learning models with traditional physics-based models, particularly in CAM. And the big idea is these are slides provided by Lorzana at the M² Lines project. So we want to develop some data-informed, interpretable, generalizable subgrid physics closures within our model. So we take either high-resolution models or observations that we trust the physics more. We build some machine learning subgrid closure, plug it back into the model. Hopefully we have an improved climate model. The second sort of way folks are doing this is learning directly from a data assimilation suite. So in this way, you take a data assimilation product, you try to see how the increments within the data assimilation step are functionally mapping from the state, and then you plug those back in to correct for structural errors, you improve your climate model. So I'll show you one example of sort of the first loop. So broadly in this project, they are pointing at the sources of errors in climate models as some of the missing or approximated physics within this subgrid state, and also some of the numerical approximations that we make. So we're trying to correct for these states. So what are the challenges in this hybrid modeling? Well, what is the truth? Do we actually trust high-res models for all processes more? What are our observations? It's really expensive to collect observations, and we know there are large uncertainties there. And then finally, there's a huge online implementation challenge. Most of these models are written in, or machine learning models are written in Python, so you have to somehow bridge this Python Fortran space connected to the GPU. It's a real computational task. So there is a nice living review put out by Tom Buchler, and you'll get the link to this GitHub here, of all sort of the space that's happening in the both emulator and hybrid. And it's a really nice repo to just look at all the literature. So I'll hand that off to you. I'll give you one example from a colleague of mine, Akesh Sain, that put out a really nice paper looking at the importance of correctly characterizing some of the parameterizations in the oceanic boundary layer. So the boundary layer captures a lot of processes. It's really, really complicated space, and we somehow need to communicate between the ocean and the atmosphere of this. So what they have done is they have currently in the GFDL model, they have a first order or first moment closure scheme called EPBL, or Energetics Planetary Boundary Layer Scheme, that communicates some of the eddy diffusivity vertically. And they know that there are better closure schemes, so they run the same model with a more computationally expective closure scheme and try to make a mapping between their current scheme and that secondary scheme. And they're doing this by mapping two parts within a machine learning framework. So they're learning a shape function based on some parts of the model state, and they're learning basically below that shape function as it moves down through the mixed layer. And essentially what you can show is that by learning a correction to their EPBL scheme, they can vastly improve the biases within the mixed layer. So this is without that correction, this is with that correction, and these are biases in the mixed layer state. So they're showing a much improved model. This has been implemented in MOM6. It was written directly in Fortran, super fast. So hopefully this is one thing that we're going to be exploring, putting into CSM. So if you want to know more about hybrid modeling, my colleagues and I put out a book. This is all using the RENS 96 system, and we show you all kinds of machine learning techniques and ways to exchange information between the neural networks and then our dynamic model, which is L96. And you can run all this code. So I encourage you to check it out. So moving quickly into the scientific discovery. So this is where we're trying to understand what the algorithm has learned about the system and try to pull out or glean some scientific understanding from it. So I spent way too long making this, but I like it. This is, you're essentially using your neural network to be an earth science detective, and really intentional question design has been what we have seen to have the biggest impact on whether you can pull out a scientific understanding. So starting at the very beginning and designing your neural network with specific intentions to learn a certain question. And I would encourage you all to check out Libby Barnes' work at CSU. She's probably leading the field in this sort of area, and her students. So really the question is, how did the neural network come to this conclusion? And what we're doing is taking some state and mapping it into the world, or our current system, and then we are going to take the gradients or the sensitivities within the neural network, try to understand which places, typically in the input space, the neural network is looking. This is one brand of sort of explainable artificial intelligence. For example, one method is layer-wise relevance propagation, and this is really trying to map the output state and try to understand where the neural network is looking. So in this case, you have a neural network that's predicting that in this picture there is a cat. We all agree? Well, it was looking there in order to see that there was a cat. So that's the big idea. So now we can apply this sort of method. We can say, let's design a prediction task, understand where their neural network was looking in order to capture that prediction task. So for example, here is a case where these explainable artificial intelligence techniques have failed. So is there a horse in this image? Yes, right? We see horses. So what do you think the neural network picked up on?
General body shape.
Body shape. Yeah, that's good. The text, right? So it realized that this photographer takes a lot of horse pictures. So whenever it saw that style of text, it predicted horse. So there are ways that you'd have to really intentionally design your problem such that you know you are not going to get spurious results. But still, this is exactly, like the machine learning algorithm will do exactly what you tell it to do. So this is you have to be very intentional with your question design and your input data. And once you run the explainable AI technique, you really have to lean on your physical knowledge in order to understand what it's talking about. So I'll show you one really good example of this. This is by Kirsten Mayer, who is a scientist here. And this is out of the Mayer and Barnes 2021 paper. Essentially what she's done is she's taken outgoing long wave radiation and tried to predict the phase of the NAO, or the North Atlantic Oscillation, at some lead time at subseasonal to seasonal lead times, and then looked back to see what the network was actually looking at. So she ran this forward in time, got a really good prediction of the NAO based on the OLR, I think 2 weeks ahead or 3 weeks ahead, and was able to, so asking what are the relevant structures, was able to pull out really nice looking MJO structures out of the back end of the neural network. So she was able to say, okay, likely it is training on the Madden-Julian oscillation. So that was one thing where she could kind of say, we already have this physical knowledge. Is that something that the neural network is representing? And then in the second sort of composite space, she identified what is potentially a new teleconnection and a lot of convection west of Hawaii. And currently they're investigating whether this and what are the mechanisms that drive convection there that then lead to a negative NAO event. So one way that they're looking at what the network has learned in order to continue to improve our understanding of the physical climate system. So lastly, post-processing such data improvement. And this is where you're taking the neural network, you're taking the output of your climate model and trying to improve it in some way. Offline, there's no interaction with the forward state. And here's a figure from one of my papers in 2019, just proving that I can dunk on this space, I guess. So what's the idea about post-processing? Say you have a forecast and initialization that's initialized every day, and you see consistently, here is the observation that you are biased too high. Well, let's say we run an ensemble of those forecasts, and consistently the observation is below where your forecast state is. You just want to learn a statistical mapping that says, let's learn that bias as a function of some lead or some conditional bias and remap the forecasts back onto those spaces. Super, super powerful idea that basically says, you know, we have stations or we have areas that we actually want to forecast. We have a grid resolution that's maybe too big from that. Now we can do that mapping, right? So unsurprisingly, this has been happening for a long time. So this is a paper. This is Harry Glahn, bolo tie, pretty cool, at the NWS. And this was his 1972 paper, introducing model output statistics, in which he took a multilinear regression. He said it was very clear to him that numerical weather prediction was the way of the future, but we needed to somehow map Z500 fields that we knew were really good to actual station observations. So he said probably a simple machine learning algorithm is the best way to do that. And this MOS system is still largely what we use in our forward forecasts. So old and boring, but very rigorous. Really, really good science comes out of this field. And there's been a lot of pushing on the statistical methods, proper scoring rules. A lot has really come out of this line of research, uncertainty. It's a really, really impressive field of research. So the paradigm hasn't changed that much in 50 years. Models have just gotten more complicated. So now rather than using simple multilinear regression, we're using forms of deep learning or random forests. For example, here's a really nice study by Sebastian Lurch, mapping or improving the CRPS, or continuous rank probability score, of station data within Germany. And essentially, he can say at all of the red points, we are improving CRPS by that percentage by implementing these neural networks. And in this way, he has actually encoded spatial information in this. So he trains on the principal components of the large-scale state along with the local information. So where is the sort of the forefront of current post-processing techniques? Currently, we're using things like diffusion models or generative models and then combining them with some sort of physical constraints in order to generate new fields based on our forecasts. So you can imagine I now seed this conditional model with a single forecast, and then I say, okay, this is 5 days out. What are all the likely states that we could possibly get out of this? I can generate, 10,000, however many images of new, this is an atmospheric river, for example, being generated, and really constrain the forecast space through this. So I will point to some exciting work out of CU Boulder by Tim Higgins using conditional diffusion models. And then we're starting to learn how to apply physical constraints to those. So with that, I will leave you with these slides with a bunch of model replacement, hybrid modeling, scientific discovery, and post-processing or data improvement papers. So if you are interested in any of these fields, these are some of the folks I can recommend. And I'll stop there and take questions.
So, less questions for right now. More of I want to talk to you later, because I saw that you do super. The math thing, not like the magazine thing. And that's something
I think everyone understood.
that's something that I read about in graduate school a lot and was very excited about. So it was nice to see it here. But I guess in terms of a question for this, you mentioned coding AI ML stuff in Fortran specifically.
Yeah.
How was it doing that with, it's my understanding that part of the phasing out of Fortran in the field is about the lack of compatibility of Fortran compilers with GPUs.
So we weren't running on the GPU for this. And in a simple feed-forward neural network, it's literally just vector matrix, vector matrix, vector matrix. So you can, as long as you're very rigid about your architectures, it's pretty easy to put that into Fortran. When it starts to get more complicated, it starts to become a pain, and that's when we look to the linking libraries. So in my work, in which we're using data assimilation and accounting for spatial scales, convolutional neural networks are logical. And it would have been a real pain to then move that to the Fortran space, especially with some of the bells and whistles that I baked in there. So what we did was we essentially had PyTorch is written on top of C. We had a C, basically interpreter, C to Fortran interpreter that pings the GPUs, and then, we didn't slow the model down, which is cool. Yeah.
Thank you.
All right, question all the way back there.
Yeah, so going from the weather to the subseasonal to the seasonal to like climate scale, what changes in your machine learning model? Because like on some high level, you're like training on observations, you want to minimize root mean square error, right? And like we know that that's different on these different scales, but what actually changes in the machine learning model?
So right now, not a lot changes. We emphasize mass conservation and energy conservation and water conservation, along with some other physical properties that we do in the back end. So that's one of the big changes. And then also our validation routines kind of change. There is sort of this mismatch between a really good next day, 2-day, 3-day prediction and like a long climate rollout. So what you do is at each model checkpoint, or there are probably 3 groups doing this right now, is you stop the model from training, you roll it out for a certain amount of time, you look at the biases, and this is more of your validation rather than the quick weather timescale variables. Yeah. So
it's pretty funny to note that we spent 10 to 20 years getting our models to be inherently mass conservative, and here we are, mass fixers are back.
Yeah, we got our mass fixers back.
Anyway, I'll take a question. No, I'm trying to spread it out here. Yeah, go ahead.
So, as you have said, there's been such an exponential improvement in the last 2 or 3 years. That's probably actually going to be a sigmoid curve, and at some point we're going to struggle to improve the ML models. How far away do you think that point is, and what do you think will be the bottleneck?
Yeah, we're seeing it now. So if you look at skill versus training time, everyone's using the Era 5. There's a whole cluster of models that's like, this is about as good as we're getting. What my personal opinion is this is where we're hitting the last mile of sort of skill using the Era 5. And what that means is it's atmospheric scientists and people who actually like fundamentally understand the physics and the processes that are going to be used to continue to increase that skill. So we saw a big jump, and now it's the hard work. I mean, not that wasn't hard work. A lot of people did really amazing things, but it's really going to be process-based understanding. And yeah, to some extent, maybe the next reanalysis product will help improve resolution, things like this, but I really do believe that it is the physics and the process understanding that's going to continue our skill improvement. So it'll be slow, and I do anticipate it. It's no longer going to be this exponential growth. It'll be slow, linear improvement, and I could be wrong. So maybe there will be breakthroughs, but I don't see it.
Thank you for the talk. I'm wondering if the ML models are basically data-driven, why they don't respect the conservation laws?
They're not inherently optimized to respect conservation laws. They're like, if you are slightly off on any, like it's very easy to break conservation, right? And maximizing, but it's also hard to get a perfect prediction. You can get 99%, ACC anomaly correlation, and still be slightly off. And then when I take that slightly off field and I pass it through another time step, like I break it right there. So if in a perfect world where we're training on perfectly conservative data, and we don't have like numerical error leaking in, and then we train our model perfectly, they would respect conservation. But that's a lot of perfects that just chain together. Yeah.
Well, that is good.
Oh, sorry.
Oh, go ahead.
Either one.
Yeah. Go ahead. Do these machine learning models face the same kind of chaos and predictability issues that physics-based models do? Like, how does this work with like longer forecast lead times?
There's a lot of really interesting research on that right now, whether they have the true upscale energy growth. There's obviously a chaotic element. We can show that if you introduce noise, it will grow, but not necessarily right now at the same rates. But there is a lot of cool work to understand like what's controlling that and how can we constrain for it. So yes, the answer is yes, but it's that you're at sort of the forefront of the field there.
Okay, go ahead.
Wondering if you think, so like the fully data-driven models have large 6 or 12-hour time steps, whereas physical models and the hybrid ones have much smaller ones. Do you think there are gains to be made from reducing the time step size for fully data-driven models, skill-wise or climate-wise?
I do. The big issue is the compute scales like crazy. So when we were running our 1 hour time step model versus a 6 hour time step model, like it functionally takes 6 times as long to get a really good fit. And then when you're rolling out at that time scale too, that multiplies the compute kind of exponentially. Some of the processes are just represented better on the shorter time scales, and we can actually see that growth and development. So like our physics understanding would tell us that like, yes, there's information there. But it becomes a really big computer problem really, really fast. So yeah, right now what a lot of people are seeing, at least on the weather timescales, successful, is you run your machine learning model and that constrains the large scale field. And then you nudge your dynamic model to the large scale field, and that carries the full state, but it's like better at getting the large scale. So does that make sense to everybody? You're running your machine learning model, you linearly relax an actual forecast, a numerics or physics-based model, back to the machine learning model at just the large scale waves. And this way, your numerical model carries all of the high frequency information, and the machine learning model does what it does really well, which is doing the low frequency evolution of the field. So
they did that with IFS, no?
Yes. Yeah.
What was the improvement, like 10%?
It's dramatic.
Yeah.
As you showed with your horse and text example, we don't understand what neural networks actually learn as humans. Are there ways to build interpretability into your networks that you're excited about for atmosphere and climate modeling?
Yeah, the way I see it is the two fields are just going to start converging on each other. So we're going to build more of the physics parameterizations into the pure machine learning models, and we're going to build more of the hybrid models to kind of, so as we build more of those physics and parameterizations, and we can lock out certain layers, and we can understand exactly what those tendencies are coming from there, I think it'll glean more understanding for what that will happen. So that's what I'm excited about. And DIMA from Neural GCM, they have built a dynamical die-core that's differentiable, and now the physics are done all by the neural network. I love that work. I think that's really exciting. So I think there's big progress there.
Thanks for the talk. That was really good. So I wanted to ask a question about climate and machine learning. I think you put a question mark there about whether we are just going to stick with the weather forecasting with machine learning models or going to move to climate stuff with the machine learning models. I want to know how far or how well are we doing with machine learning studying the physics of the climate model and trying to conserve energy to make sure that we are getting there?
Yeah, it's a great question. We're doing all right. We have, I would say, the big examples of this are the Allen Institute, and Chris Brotherton is leading that group. We have a project here going on emulating CAM, and there is Lucy. Do you know where Lucy's out of?
Penn State.
Penn State, okay. And these are the three, are you a Penn State person?
Yes.
Person pride and not Penn State. I would say these are sort of the three at the forefront, and they're doing their best. But I think what's going to happen is we'll understand how we will use them. Maybe it'll just be for ensemble development. We can say the variability of the 500 fields look great, and we want to constrain signal to noise studies around things like I think they will work in tandem. Right now, full model replacement, it's a really hard task. I think people are working on it. It remains to be seen whether it's going to work and we can fully replace things, but remember, we're training off dynamical models. We'll never get rid of them. So, yeah, big question mark is what I'm saying. But really, really smart people and really good people in our field are working on it right now. So it gives me faith to be like, yeah, this is an exciting area to explore.
Okay. Owen?
Not to put a point on it, but what's in it for the tech companies? Why are they in this space? Particularly, why are they collaborating with academic people? What structural factors are leading to these collaborations?
NVIDIA sells GPUs.
Yes.
That's not their only reason. That's not their only reason. They're very. It is a good proof case for them.
Sure.
They've also taken people from atmospheric science and they want to make the best product. I genuinely believe they're acting in good faith. There is profit there, but also at the same time, like it is fundamentally one of the most interesting problems, right? Predicting fluid fields. So when, for example, when DeepMind was thinking about, are we doing, what's our next big problem to test, to stress our really big models on, is literally the motivation was like, man, weather's really interesting. Like the fluid fields are really cool. So they thought about like really idealized LES, or they thought about weather and they chose that. So the motivation, I think, it remains to be seen. Like there's a big industry there that you can forecast the weather on, but there's not a lot of money to be made there. We get our forecast for free and
Right now we do.
yeah, right now we do. So I am a big, like my inherent belief is like I'm like man, industry's bad, but the more I've interacted with these folks, the more I just believe they are interested in the problem and they're trying to help. And that is pretty evident by the fact that they're gonna come here and like talk to us and like release their models. So yeah, I can be a skeptic, but they're winning me over.
We were just talking about right now we get our weather forecast free. That kind of reminds me, and for machine learning, so we're training them on these models, right, which come from observations. I wonder how the machine models are going to work, whether they work better in the absence of certain data. For example, we're not doing balloon soundings in certain places. We could have a satellite go down. How well will the machine learning models adapt to that lack of information if we're using them in an operational forecast?
Yeah, a lot of folks right now are using the traditional assimilation systems, taking that analysis, running them forward in time. So our traditional models will degrade, and our initial conditions will degrade. It's hard. It remains. We haven't done data denial studies with the machine. Or I haven't seen them yet with the machine learning models. So it's possible the forecast will degrade, but if we lose observations in our simulation, our traditional forecasts will degrade also, and we're building off those. There are systems that are moving end-to-end, observations to observations. There are systems that they're now using machine learning to do mappings with the data assimilation. But yeah, we will get degradation if we don't observe the atmosphere. We need to observe the atmosphere and the ocean.
Yeah, I'm not doubting that. I'm just wondering who's going to degrade worse, machine learning operational or the traditional model? Yeah.
Okay, last question. Somebody who hasn't asked a question. I'm looking at you.
Yeah, great talk. My question is about loss functions, because it seems like your choice of loss function, like whether you optimize for like mean state or more granular features, can like really impact things. So I was wondering like what is like the popular choice, and like if this is an area of improvement.
The popular choice is mean squared error. A lot has been invested in trying to understand what are better loss functions. For example, using spectral properties in order to try to boost the areas that were the resolved dynamics. Sometimes you can just compute your way out of it. Like that's the biggest thing right now is like bigger models are doing better. But I think if we start to do more, there's been a lot of loss function design. I don't know exactly if everyone has settled on a really popular choice. Like if you're doing it probabilistically, CRPS, like a proper scoring rule, makes a lot of sense. but then you can penalize other things too. So yeah, there's area, there's room there, but it's a lot of people are thinking about it.
All right. Well, thank you, Will. Let's give my All right. So now it's time sleeves to actually run the model. Unfortunately, Sizzle, who runs our computers here, decided to take down our biggest CPU cluster exactly this week. So we're going to run on a machine called Casper. We really, really hope it's going to work out. It's not going to melt down. So unsafe. But to prepare for that, is Christian, and I think it's a joint talk with everybody on the list here. Go ahead.
This is now giving you really information about the depth of DCMIP and hands-on portion.
And well, Adam and I were just actually interacting with Sizzle because some portions of Sizzle are already, or the Casper cluster are in trouble right now with overheating issues. So I think we have a solution. I think Adam will try it out. So bear with us. These hiccups could happen this week as we see, as we stress the cluster a little bit also when we get going this afternoon, right? So this lecture will be, it's a joint lecture. You see a lot of names here, and I will just say a couple of intro words, and then I will give the word to Tim and Owen and others who will then really dive into the characteristics of the test cases and kind of provide a big overview of the theme. Yeah, so it really sets the stage, and you know what to expect. I know that we have a really diverse audience. Some of you are from atmospheric science, others are from mathematics or computer science. So it's not that everybody understands all keywords. Yeah, so this hopefully at least sets the stage, and also you can, I think we mix the groups, hopefully good enough or well enough, so that you can interact also in your groups or with your mentors to maybe clarify a couple of concepts, because there are concepts from atmospheric dynamics here. Gravity wave motions have some theory behind it, and we allude to that a little bit here in this presentation, and you have a chance to explore more. Yeah. Right, okay, this is a slide I presented earlier. Yeah, so we are using, remember, a couple of die cores, SE, MPAS, and FE3. And then we have the machine learning emulator, which is a little bit of different flavor, but you saw already Greg Hakim's, or Will actually showed you a slide from Greg Hakim, and that's where we draw the inspiration from. So Josh will actually talk about that here towards the end. All right, we have four science team, including machine learning. So we will be looking at those topography flows. Yeah, so this is number 1 and 2 here. With number 2 has 2 options, gap flow and vortex shedding. And then we look at the coupling between physics and dynamics, which is the squall line test case. Okay, maybe also to set the stage a little bit, we are looking at various grids. Adam did a really nice job introducing some ideas, how we can model the sphere. And those will be the talking points also for DCMIP. So you see now, here are now the 3 die cores. The spectral element die core here on a cube sphere grid, in the middle the finite volume cube sphere die core. And it does look alike. They are actually not the same. Its differences are small. It's not really something you can detect by eye, but here we already look at 2 different concepts of cubed sphere grids. One is called the equiangular cubed sphere grid here with the spectral element die core, and then in the middle we have a version of the cubed sphere grid which is called the equi-edge cubed sphere grid. And if you really want to dive deep into this, then Tim would be the person to talk to, because he just put a manuscript together about those characteristics. Right, and then we have MPAS. MPAS, I also would call that a hexagonal grid. I guess technically they call it a centroidal Voronoi tessellation. And it has an ability also to adapt. We don't exercise that option, but it can adapt its resolution. So a variable resolution mesh option is also available here for the, I use this as a pointer here for the MPAS grid. Okay, so I'm debating whether I should click on it now or maybe come to it after maybe you saw all the test cases. So the DCMIP webpage here, you kind of see the link. will be your tool to get all the information for the hands-on portion. For example, how to get a configuration into your own directory, how to compile it, how to submit it for execution, and also we have pointers to Jupyter notebooks and some visualization hints. We will have, maybe as a heads up, tomorrow morning, the first morning, half an hour actually, we also devote to data analysis and visualization tips that we want to give you. Yeah, so these are, we probably can touch upon very, very briefly today when we go to this webpage. But maybe let me table that. I also don't quite know how long the discussion will take, the test case discussion. So maybe we come back to this webpage. We click on it kind of more towards the end of this segment. And maybe as a heads up, we did schedule a little bit more than an hour for this segment. Yeah, so lunch will be 12:45-ish, yeah, so bear with me if you get really hungry. Maybe there's still some snacks outside, yeah. So we just wanted to make sure that we have enough time to give you a good description of the test principles and also have a little bit of time here to click on the webpage because this is really information you need in the afternoon, right? Okay, maybe I then I think Owen is the first one. Let Owen talk about test one, and test one is about gravity waves. Do you want to go over this or shall I share? Okay, maybe I just do this one. And this sets the stage for test one, which is based on ideas that Owen had evaluated in some of his test case designs earlier. But let me maybe just walk you through. And this is for those who are atmospheric scientists, maybe you've seen this. For those who are not atmospheric scientists, maybe the first time to see gravity waves in action. And I just want to give you a little bit of an idea what gravity waves do. Yeah, let's maybe go here to that diagram. So this is actually a 2D simulation by Dudia. He's actually a scientist here at NCAR in M3. And depending on your characteristics, and I mean, let me maybe guide you to this here. Characteristics means of the flow field, of the background condition. And when we talk about fluids, then we talk about a wind. U is a symbol for the zonal wind. Yeah, this is the west-east component. N, if you haven't seen this, is called the Brandt-Weisler frequency. This is a symbol for, or not a symbol, but this is a definition of static stability. You want to have this positive, which you see here, and this is a very typical value of static stability. This is a positive static stability here, which we would also find in nature, in the troposphere. F stands for the Coriolis parameter, which is rotation. Yeah, so this is nothing but 2 omega rotation rate of the Earth times on the sphere would be times sine of the angle of the latitude. Here, this is actually not an issue because it's kept constant. So the Coriolis parameter here is just basically considered to be for a plane. But this value, as you see it, it's a really good value for mid-latitudes. Yeah, 10 to minus 4. And then we have the height of a mountain. And that is, for example, here, H0, 400 meter peak height of a mountain. For example, you see the mountain a little bit here. This is kind of a Gaussian mountain, really smooth looking. And with that comes a good parameter which you should take note of, which is called the fruit number. So maybe, let me see hands. Who has seen the fruit number? Okay, maybe a third. Oh, okay, so if you haven't seen it, this is Gravity Wave 101 here. This actually determines a lot of the regime that we are in, the kind of the flow response regime. And you see now how these parameters come in. U as a wind, and then N, the Brandt-Weisler frequency, and H. And here with this, we are in a so-called linear regime. If your fruit number is less, the 1 is kind of a dividing line. So if it's more than 1, it's linear. And if it's less than 1, it's nonlinear responses. And what it means is that your gravity wave should be very smooth looking linear. So gravity waves are these guys. Yeah. So actually here we are seeing the vertical velocity. These are contours of vertical velocity. And, oopsie, it was too quick. You basically assume that the flow comes, this is just a cross section, but the flow meets the mountain, and then deflections happen, and that leads to wavy motion, and this is gravity wave motion. And this is a typical signature. These signatures are contour lines of plus minus vertical velocity. Yeah, so these are upward propagating. So we see, in this case, we see, this is a vertical cross section. Yeah, so it's a vertical, and here X, basically the X dimension. Okay, and then depends, and this kind of comes down then here to these different boxes. What is the flow doing? And the flow is very sensitive basically to the settings, and especially here again, this is 2D flow, in our case will be 3D mountain. Here you see definition of the mountains. It's actually Bell-Loffer-Kniesi curve, I guess there's actually a term for that. And this is just kind of pretty smooth, like a Gaussian mountain almost. But you see, here are a couple of parameters. Again, our mountain looks a little different. I'm just using this as, for explanatory purposes. But here, if you change these parameters, and especially A, you can be in very different flow regimes for the gravity waves. And that's something to be aware of. And I will show you, and Owen will show you where we will be in DCMIP. Okay, but if you are really small, if there's basically, these are now spatial scales. Yeah, so in the horizontal, you can, of course, later also change H naught, just the peak height of this mountain. But let's look at spatial scales. So if you're really small, you are basically doing nothing. Yeah, there's very little response. If you go a little bigger, and bigger means, for example, with the mountain shape here, you go to like a 1 kilometer scaling, then you become, or you get into the mode of a non-hydrostatic gravity wave motion. And that's interesting. Oh, look, I'm a little bit too quick here, because this is a slanted gravity wave. You see it slanted from the mountain upwards. And that's very different than the next one, and that is a hydrostatic gravity wave response, and that's where we are. Yeah, actually not quite. Maybe I should be more precise. We are, and this is kind of the difference here between the hydrostatic and an inertia gravity wave response. We are actually so big, this gravity wave is so big that Coriolis forces, inertia, comes in. Yeah, so we are actually in this mode that we are not quite straight up. You would be. This is probably not the best idea to do with this particular test case. You would be straight up without Coriolis force, but since we are turning on the Coriolis forces, we are actually in a regime of inertia gravity waves. So these waves, yes, they go up. They're also a little bit slanted. They do look different, though, than those pure non-hydrostatic gravity waves. Those guys, at these really small scales, would also not really be impacted by Coriolis force. Too fast. All right. And if you really go big, which we don't, you would be in a regime which we call the quasi-geostrophic regime. So that's maybe not a topic for today. Just want to mention, you should expect gravity wave motion that probably has, has kind of signatures that are here between the hydrostatic and the non-hydrostatic regime. And we will be in this is another difference to this example, we will be in a nonlinear regime, and nonlinear regime means we should expect braking, gravity wave braking, and that's exactly what we want to see, and also want to see what the models do with this braking signature, because models have a little hard time resolving wave braking, and diffusion will come in, and diffusion will work on the braking, and that's all up for grabs. Yeah? So I turn it over to Owen, who kind of does deep on this.
Can people hear me? Great. Okay. So this is sort of based on a incremental addition to a test case that I worked on a couple of years ago. The idea is basically I'm going to introduce some jargon here. When I say zonal wind, I mean east-west wind. When I say meridional wind, I mean north-south wind. And this test case is based on a base state, meaning that is a steady state. That is, this is there's a form of, or a solution to the equations of motion that does not evolve with time in the absence of topography. So the idea in this test case, and it was originally sort of turned into this form in the Ulrich et al. 2014 paper. With that one, you add in the old version, you add a temperature perturbation, and that basically, due to the structure of the atmosphere and that zonal jet, you end up with what's called baroclinic instability. So that's a common feature of the large-scale atmosphere that basically leads to planetary scale waves when you perturb it. In the old one, you add a temperature perturbation. And in this test case, we add basically 2 mountain profiles. Here I'm showing surface height. Basically, it is a quasi-Gaussian profile. It's been extended in the meridional direction so that there is the peak is better represented in different grids. Basically what happens is that this perturbation induces a growing planetary scale wave, but it also induces gravity waves moving vertically. And so that was the original test case that we talked about, or that was published years ago. And in this one, we make a slight modification to the temperature structure where we add an idealized stratosphere. Basically, in the original test case, temperature continues decreasing with height to the model top. And in this one, we modify the temperature so that it is still a stable base state, a stable steady state. But in this case, you end up with this increasing temperature such as you observe in the real stratosphere. And what that causes is basically, so this is the Brunt-Weissler frequency. If you're not familiar with it, it's basically the squared period of oscillation of a perturbed parcel in the atmosphere. So basically, in a stably stratified atmosphere, if you sort of wiggle a little bit of the atmosphere, it will oscillate with a particular period. This is the Brunt-Weissler frequency. We show the squared version because that's it's typical. So in the old version, the Brunt-Weissler frequency continues sort of changing gradually as you go up in the atmosphere. And with the addition of the stratosphere, you end up with this kink in the Brunt-Weissler frequency, which means that basically a parcel perturbed up here will essentially, it's frequency, so it will oscillate more quickly than down here. And the other addition that we make is that we add Rayleigh friction sponge layer in the upper 10 kilometers. So in DCMIP, you often want things to be as apples to apples as possible. So the modifications to this, to the cases you're going to be running, try and reduce the internal model sponge layer that Adam talked about, eliminate those mechanisms, and instead we use a Rayleigh friction, which is a relaxation, just basically like the standard ODE decay to known state. In this case, we relax the upper 10 kilometers of the atmosphere to the initial state of the initial base state, because if we damp it to 0, that actually disturbs the base state and causes spurious circulation at the top. And so the idea here is that we are testing vertical grid spacings. So in an atmospheric model, the vertical is often pretty different than the horizontal. And what we're looking at here are increasing resolution from sort of a typical resolution of like less than 100 levels up to 200 levels in 40 kilometers, which is very fine for an operational model. And looking at the characteristics of the wave breaking that's induced by this kink in each dynamical core, how the design decisions and choice of diffusion and advection and all of these things impact the wave breaking. So in terms of the characteristics of this initial condition, the easiest to interpret thing is on the right here, which is basically the characteristic vertical wavelength of a wave can be calculated based on this left quantity, 2 pi over the square root of that quantity. And what you see is, like I said earlier, you have these long wavelengths in the lower part of the atmosphere, and then when you reach this kink, the wavelength goes very small. becomes very small. And so what happens is a vertically propagating gravity wave, when you start getting those shorter wavelengths, you end up with wave breaking, things that are too small for the model to resolve that cause overturning. And so what we're looking at is basically how does that breaking look different in different models at different vertical resolutions. So what I'm showing here are potential temperature contours in the black lines and then horizontal divergence in the colors. The 4 kilometer mountain peak. In the original test case, it was 2. We've increased it to 4. And so what we've observed across models right now is with sort of the base configurations, if you run at with a maximum grid spacing of 800 meters, that you don't resolve very much of the breaking. Basically, you have an inertial gravity wave signature up to the stratosphere and then kind of nothing above it. And what you see when you go basically set the maximum grid spacing to 200 meters is you start seeing more of this breaking being resolved. And sort of non-monotonicity of potential temperature tends to indicate overturning in the atmosphere. And we're starting to see that in the 200 meter, which is closer to converged. Basically, if you go to a maximum grid spacing of, or vertical spacing of 100 meters, it looks pretty similar. So the response looks very different in different dynamical cores, which is sort of the point of these test cases. This is FV3 with the default diffusion settings. And what's basically shown here is that the divergence values that we're seeing are slightly larger. There is some stuff happening downwind of the mountain that is a little bit noisier and harder to interpret in the 800 meter run. And then in the 200 meter run, you end up with a lot of signature. I uploaded a new version of this, but it doesn't appear to have loaded. So your runs will look a little bit different than this. But basically, what we found in testing was that diffusion properties really impact how these simulations look. And that it's quite likely that looking at different design characteristics of the dynamical cores will change, particularly what this breaking looks like. I haven't actually run 100 meters in FV3, but I can set up a case for that really easily. The Richardson number is another derived value in atmospheric science that indicates, or just fluids generally, where a Richardson number less than 0.25 indicate potential turbulence. And what I'm showing here is sort of the SE dynamical core. This is 200 meters, so we expect to see sort of this diagonal pattern. Has somewhat smoother pattern or regions of overturning, and then FV3 you have this very grid pointy stuff going on there, which is likely very sensitive to diffusion. And the question is basically, are there values and configurations that cause these to look very similar? Is this inherent to the numerics? Is this an artifact of the artificial diffusion that we add in? All of these things are what you're going to have the opportunity to explore. So that's basically the summary of this test case. And I will turn it over to Tim.
Cool. Yep, so the second test case is also to do with topography. So whereas where test case 1 was more looking at effects in the vertical direction, we're more looking at flow in the horizontal, or what happens in the lee or after the flow goes past the mountain. So we're again in a very hydrostatic regime. And we'll be looking at 2 different configurations. So these only vary in the shape of the topography. So we have the first being flow through a gap, and the second one being vortex shedding behind a more circular mountain. So these share a lot of common features between the two test cases, which is why we group them together. The first is that we're now using a small Earth. So where the first case was on the regular Earth, we moved to a small Earth. And this is so that the features are more alike in reality. So this means that the radius of the Earth is actually reduced, so approximately 320 kilometers. So we have an isothermal atmosphere, so we keep temperature constant throughout the whole vertical profile. And this leads to a constant static stability of very close to 0.1, so it's 0.018, sorry. We again have a solid body rotation for the velocity field, where we have it varying with cosine of latitude. The benefit of doing this is it means that it goes to 0 at the poles, as you don't have any issue with the pole points. We have a model top of 30 kilometers, and the vertical grid is actually stretched. So the feature of interest is around the mountain, and we need to have a sufficient resolution over this. But we don't want to have to then have more computational expense at the top of the model where we don't really care about it. So we actually stretch the model above the topography. And in fact, half of the model is a Rayleigh friction layer. So the top 15 kilometers, we're trying to absorb those vertically propagating gravity waves. So whereas in the first case, those were of interest, in this one actually we want to kind of suck them up. Otherwise we get reflections from the top of the model, and this kind of comes back and affects both the gap flow and also the vortex shedding. So that's quite a tricky part of getting this model, this test case working. Lastly, the default topography will have a peak height of 1.5 kilometers, but this is a factor that you can play around with, and you'll see different dynamics depending on the height of the topography. Okay, so the first variant is the gap flow. And one inspiration for this is the Gulf of Tehuantepec, I don't know, in Mexico, where you see that the winds can kind of accelerate through this gap a lot. And in the Gulf, you get very strong winds. So we want to kind of model this flowing through some mountain chain. So we are in, again, a very non-hydrostatic regime. So the Froude number is quite a bit less than 1. So this is something you can also play with. So if you change the flow velocity or the mountain height, you'll be affecting the Froude number and you'll be getting different dynamics appearing. So the functional form of the topography is actually very similar to what Owen had. We chose using exponential functions, so you can actually differentiate this if you want to create an initial condition for your vertical velocity. We have a few different parameters that you can actually play around with to change the shape. So we have these E coefficients, which kind of determine the shape of the slopes. We have these D coefficients, which are length scales, so how long does the gap kind of extend latitudinally and also longitudinally, and also how wide is your gap. And something to note that when you're defining these, remember that we're on the smaller Earth. So these values are 20 times smaller than on the regular Earth. So I have some default settings here, and these can be easily changed within the initial condition, so you can play around with different gap flow, gap sizes, and see what happens to the flow there. So in particular, what happens when you have such a really long gap or quite a wide gap? What happens to the flow in that case? So I've just got a couple of cross sections of the gap. So on the top one here, we have a slice at a constant latitude, and here is a slice constant longitude. And you can see that the gap, one important feature is that we're resolving this sufficiently well, so that we have a few points within the gap region. One interesting point you can see actually that the impasse model, if you take slices, you don't get a symmetry of these points, and this is because it's on that Voronoi grid. And so it's not actually symmetrical around the equator. So this will be a difference you'll expect to see between the two different models, whereas SE and FE use the cube sphere, which is symmetrical around the equator. Okay, so a couple of things you can do with this. So one, we're looking at also with and without Coriolis forces, and this will change the dynamics you get through the gap flow. So hopefully these videos will play. But an example of flow through the gap with the Coriolis force. What just happened there? I've got a video coming up on the screen here, but I don't think it's come up. Oh, okay. But then it just. Okay, here we go. I'll try pause it towards the end. So we're plotting the wind. So the blue lines show where you actually have a deceleration, or sorry, actually a reverse flow. So these are actually the velocities of overturn. So it's coming in here, it's 10 meters per second right through the gap. And at these points here, the flow is actually turning around and going back the other way. And these red regions show where you've actually got acceleration of the flow. So the flow is accelerating through the gap, and you're also overturning on the other sides. So that's the case with Coriolis. Okay. And then without Coriolis, okay, good. You get quite a different feature. But you get quite a pronounced acceleration this time, and you get a lot less of that flow reversal. So there's definitely quite different dynamics depending on whether you do or don't have that rotational force. Sure. It's, no, it was this one, wasn't it? No. It's hard at this angle to see it as well. And so part of what you'll be doing as well is we have some visualization scripts where once you run it yourself, you'll be able to make your own videos and sort of play around with different fields to plot and things like that as well. Cool, so of course we're wanting to try compare these models, and here's just some preliminary results, I think running with a model a month ago or something. But you can see some definite differences between the spectral element, finite volume cubed, and the impasse model. Specifically, there was quite a bit of asymmetry in the impasse model. Potentially, there wasn't sufficient resolution in the gap. And so if you increase the resolution, that asymmetry might be removed a bit. But yeah, this is definitely something to be looking into when we do the afternoon's activities. And again, showing the case with rotation has different dynamics. So there's definitely a few things to play around with. I won't go into this too much detail, but flow velocity, mountain height, all things you can be looking at, and also moving the gap off the equator. That will introduce some asymmetry into it, and so what happens with that gap flow. So the second test case is this idea of vortex shedding, where we actually see this in reality, where satellite observations behind islands, you see these what are called von Karman vortex streets. And these are basically due to some imbalance of the flow on either side of the mountain, and that creates these vortices kind of interchanging and creating this field. So we tried to get topographical parameters that kind of mimicked some of these mountains in reality, as specifically the Madeira and Gran Canaria mountains. And so this is part of the reason we went to that small Earth, is to try and get a nice ratio of the height to the diameter, which would be like in reality. So we modeled this using a simple Gaussian mountain. Something you can look at is maybe changing this to an elliptical profile. I think Gran Canaria is elliptical. Again, these parameters are the same as in the gap flow case. So trying to keep this thing relatively simple. So the difference is just in the topographical profile. We also now have the Gaussian at 20 degrees north. So it's offset from the equator. In fact, this is part of what instigates the von Karman vortex street, is you have asymmetry in the velocity over the north side versus the south side of the mountain. So again, just a video of what happens. So, come on, okay, cool. This time we see some alternating vortices forming behind the mountain. We do have like a better, more recent visualization, but yeah, something you guys can play around with. And just to compare the different die-cores, so from preliminary tests, I found that the results were quite different between the dynamical cores. Specifically, the FE3 model was having a few issues still with reflection of the model top, and you can see its kind of peak values were affecting the vortex street. SE kind of had the nicest picture at the moment, but it'll be interesting to see what happens with changing the parameters. And again, this test is very sensitive to diffusion mechanisms. And actually with FE3, there are a few optional extras we had to add in to keep the run stable. And so that'll be a lot to look at, will be how much the diffusion impacts the representation of these vortices. So this is a comparison now of the velocity field. And you can see regions of flow, reversal again, and also acceleration. So again, very similar modifications you can do in this case, such as changing the topography. Something I probably didn't mention actually the first time is that the SE and the FE models, you can easily change the topography. MPass is a bit of an outlier with this. So you actually have to generate topographical files offline, import it in. So it's a bit more difficult in MPass to play around with. But there's still plenty of other things to look at. Specifically, there's lots of diffusion mechanisms in MPass you can vary. Yeah, are there any questions about those two cases? Yep.
Sorry, when you said that.
Yep.
Do we also want
You could have a look at that as well, yeah. I can show you where that is. That's we implement it as like an optional physics package. So it's a different routine to look at. But that's definitely of interest and is very important for this case. So I think it's interesting to look at. Cool. If not, I'll pass it over.
Thank you.
Everyone hear me? My name is Nick Androsky, and I've been working on the squall line test case. And so this one's kind of going to differ a little bit from the previous two test cases. One, in the fact that we are looking at smaller scales than the previous ones. Small enough at the kilometer scale that we'll need to account for non-hydrostatic motions. And so that requires, we can't use the hydrostatic dynamical cores to model this because of the large vertical accelerations that are being produced in this test case. But the main idea, if you're not unfamiliar with the squall line, it is a line of organized zones of convection. And they are very common in around this area. And in the US, to the east of the Rockies, they bring a lot of enhanced winds and precipitation. And as I was mentioning, they are operating on around these kilometer scales, and they extend over 10 to hundreds of kilometers. As Adam mentioned, even if we're resolving even if our grid scale is at a kilometer scale, we might not be resolving at the kilometer scale. And convection, which is a very important part for the squall line, occurs on a whole range of scales. So in many ways, this is a great test for the dynamical core to see how well it is resolving convective motions in an ideal scenario. So an important thing for a squall line is it needs a few ingredients to get one. You need to have static instability, unlike the previous two test cases that had stability in the vertical, where when you displace a parcel, it will oscillate. In this case, we need something that's unstable, so when we displace the parcel, it actually wants to accelerate. And this creates updrafts, and large vertical accelerations that create these convective processes. And another important ingredient for producing the squall line motions is having a low-level vertical wind shear. So a change in the zonal wind, in this case, over the first 2.5 kilometers of the atmosphere. And that's just important to have the environment to even get a squall line in the first place. The squall line test case it's a good test for the dynamical core in terms of testing the non-hydrostatic motions within these dynamical cores. It's requiring these high kilometer scale resolutions, which a lot of these die cores are beginning to. Sorry, do you have a question?
Yeah, is that the infamous 98 duration?
No, this is more. This is maybe from 2020 or 2021. I got this from a friend of mine. It's over the Ann Arbor area where we're at in the University of Michigan. Just as a little example. But I myself don't have too much of a background in atmospheric or weather, and so I would be interested to hear about this infamous case. As I was kind of saying, we're going to be operating on the kilometer scale resolution, and a lot of these non-hydrostatic dynamical cores are starting to be applied at global kilometer scales, and so it's an important test to kind of see how these how they're working here. In addition, we also want to model precipitation from from the squall line, and so we're also testing the kind of physics dynamics interplay that is happening at the grid scale for this test case. So for the squall line initial conditions, we're basing this upon a previous DCMIP test case from 2016 that's on a supercell, which is a large, long-living thunderstorm system. I'll kind of explain the differences that we're doing from that supercell test case. But overall, there is a hydrostatic cyclostrophic balanced initial state, and this is the balance that we expect for an atmosphere without rotation. Similar to the previous test case, we're using a reduced radius Earth, about 1/60th the size of the normal Earth, and that way we can get kilometer scale, around 2 kilometer scales for a 1 degree grid without a lot of computational expense. So we can actually model non-hydrostatic motions here. And we're also doing we're using no rotation for this test case because these squall lines typically at the scales they happen, the time scales and spatial scales, Coriolis force isn't as significant to the motions, and so we don't want that impacting the results here. And as I mentioned, we have this first plot here on the left is showing the zonal wind profile that is analytic. So we have a kind of a linear shear region at the bottom, and it transitions into a constant wind up for the rest of the atmosphere with a smooth transition in that kind of pink region. For this test case, we're using a smaller model top. So instead of the 40-kilometer model tops that are used in the other test cases, it's lower at around 20 kilometers. So it's mostly resolving just the troposphere with a little bit of the stratosphere, which we just kind of assume to be, or we have it set to be isotropic in the stratosphere. But a lot of the action is happening kind of within these first 5 kilometers of the atmosphere. And so as I kind of mentioned, it's important to not only have this zonal wind shear, but we also want an unstable thermodynamic background. And so we're doing the same profile used in the DCMIP test case, and also based on a previous supercell test case from Klemp et al. In 2015. That this sounding here on the right has a high amount of convectively available potential energy, which essentially means that it has a large amount of instability. And this is typical of severe Oklahoma squall lines. We're having the environment to produce a squall line, but to actually get our squall line, we need to have a good trigger for it. And so to trigger it, we're going to use this warm bubble perturbation. So we take the environment and we're going to add a temperature perturbation on top of that. So for the supercell test case, this was just one bubble that we would add, and that would create this large zone of convection. But for the squall line, really the biggest extension is we're just going to add more bubbles, and they'll eventually start convecting because of this warm air will kind of trigger this acceleration of the parcels and start to kind of collectively organize into a squall line. So I've been, in my tests, I've been using about 9 bubbles that are spaced about 6 kilometers from each other and are about 3 kilometers wide and about 1.5 kilometers, or has a vertical radius of about 1.5 kilometers. There isn't necessarily a reason why it should be this. So that this can be something that can be messed around. I don't really know how much this, the spacing, the size of the bubbles, the strength of the perturbation, which is about 3 Kelvin here, can actually, I don't really know how much that affects the ultimate squall line there. So it's definitely a big thing that can be tested. It is really testing how the trigger will change the ultimate squall line. But yeah, so with these, so we have the environment for a squall line, we have the trigger for it. We also need to model the microphysics, the physics here. And so we are using a very simple physics scheme here called the Kessler physics, which is just a simple warm rain water scheme that kind of tracks rainwater, cloud water, and water vapor. So there won't be any snow or other types of forms of precipitation here, just rain. This Kessler physics is already something that's built into the ideal physics schemes that are in CAM. We've just additionally add another variable, a radar reflectivity variable. And for those unfamiliar with radar reflectivity, it's a common measurement used by weather radars to as a measure of precipitation, and it is often what you see in weather radars. So kind of plots like these are reflectivity maps. And so we've incorporated that by using a common Marshall-Palmer relationship that relates the rain rate and the radar reflectivity Z. And we're measuring it in a logarithmic scale because it scales very much with the size of the rain droplets. So you can get a very large range of scales. Here, kind of going, in this case, we're having -20 all the way up to around 60 on this log scale. And yeah, it gives this 3D field that kind of shows the structure of your squall line and where precipitation is happening. And in this case, this is kind of a snapshot of the squall line at a 1 degree resolution with the spectral element dicore. As you kind of go from left to right, you can see the bubbles starting to produce precipitation and start to organize together. And you can start to see as it develops, starts to grow this kind of bow-like shape, which is very typical for a squall line. Yeah, and we can intercompare this between the different models. And so this is kind of, this here's the last time snap. We're running this for about 3 hours. You can already see that there are a lot of differences between these models. As Owen was kind of mentioning, ideally we want to have a very apples-to-apples comparison between our models whenever we can. The difficulty here is that diffusion has a very large influence on what the squall line that we observe. And the diffusion settings that are in each model differ greatly. And the type of sponge layers that I'm using in these models aren't necessarily the same. There is a lot of differences within how diffusion is being treated that could lead to differences between between the squall lines. And you may also notice there is these kind of features here that especially you'll see them more, particularly in FE3 across the whole domain. These are not associated with, these are not physical. They're not associated with the squalene itself. It's more something that's called grid imprinting that can be due to instabilities in the from the diffusion and in the integration of these models. And typically you'll see them follow almost like the grid lines of a cube sphere, or particularly you'll see them at the poles as well. And these are more grid impacts. I've tried to mitigate them as best as I can, but that might be a job for people out here, is to test what kind of diffusion settings and time stepping would best mitigate these effects like grid imprinting. It is particularly bad in FE3. You will likely see it, especially if you go to the half-degree models. I had to make a lot of different decisions compared to the other models just to make it stable numerically. Whereas SE and MPass, I've had a little bit of an easier time with, but there's still a lot of options with MPass, and even changing the sponge layer, the Rayleigh friction sponge layer, had a large impact on the MPass grid as well. And hopefully this will continue to loop over time, and just you can kind of see the development of the squall line. You can kind of see that each of them do have some similarities where they are kind of developing a similar bow echo shape, but and you can also kind of see the asymmetries in the MPass grid, which, as Tim was mentioning, comes from the asymmetry about the equator, just due to the Voronoi mesh where SE and FE3 have symmetric cube sphere grids over the equator. MPass does not, and so at lower resolutions, you may see these asymmetries within the squall line itself. Yeah, so lots of different ways to modify the squall line. You can take a focus on the diffusion and the sponge layer. So they each have a variety of different options, particularly FE3 and MPass. Things you can look at is how these can affect model convergence, numerical stability, and grid imprinting. You can also do a focus on the squall lines itself, affecting the warm bubble perturbations to see how that influences squall line structure, the strength of your updrafts, how much precipitation you're getting. So you can change the number of bubbles, the spacings, the size. You could make them. You could put it off. Currently, it's symmetric about the equator. You could move it off of that and see if that causes any differences with the cube sphere grid. You can also change things like the background environment. So how much shear are we having if we extended the shear over a larger region instead of the first 2.5 kilometers over the first 5 kilometers, for instance. Or you could modify kind of the initial surface temperature or tropopause temperature. And one thing I almost forgot to mention is that while a lot of these test cases here have been completely analytic in their initial conditions, the squall line is a little bit different, where we do supply analytic zonal wind profiles and equatorial temperature profiles, but we kind of do an iteration to achieve a hydrostatic balance and the cyclotrophic balance. So there's not I have an equation that tells me exactly how all my initial state is. There's this kind of iteration procedure that may change it. That may change the initial conditions. Well, I guess they can. They're not going to be exactly how the analytic. Some of the analytic variables, they might be different from what you expect. You can kind of see here, this is the dew point temperature, which is pretty smooth before this kind of iteration process can become a little bit, can change a bit in the stratosphere region. And so whether that has an impact on squall line structure, I'm not too sure about, but just something to keep in mind. while you're running these models.
So does that iteration profile include the bubble?
Yes. Yes.
So that's what that is. Adjusting.
And I have tried it with and without the bubble, and that thing is still present, and so it might be an iteration just on the initial. There's an analytic, humidity profile, but that's it's put in. They iterate it to get a nice hydrostatic balance, where that analytic profile maybe wasn't ideal to achieve that hydrostatic balance, and so there's definitely a lot of differences here because. We're shooting for non-hydrostatic motions, yeah, something to keep in mind. And with that, I'll take any questions.
Is there any convection scheme active here, or is it just the
We're just letting it be resolved by the dynamical core, so no parameterizations for convection or anything like that. Mm-hmm. Yes. Can you say that again?
How sensitive?
That's a good question. I'm not too sure. I haven't really. I've been using the same surface temperatures that were used by the DCMIP test case, so I haven't really tried varying that. It is initialized with. Initially, it has a fixed surface temperature. That can change after we do iterations and add the bubbles in. They might not necessarily be the same surface temperature across the whole domain. Not quite, yeah. Yeah.
The algorithm for hydrostatic balance, is it the model's discrete hydrostatic balance or an analytic formula that you're...
It is a discrete, so it's iterated to machine precision. So that, I don't know if that could also bring issues in numerical stability. Okay, and with that, I'll pass it off to Joshua.
Okay, hi everybody. Thanks for the great introduction. And actually, I want to start off with just some thanks to people. My two primary collaborators in these machine learning test cases have been Travis O'Brien in the back. He's my advisor in my master's degree, and he's been super helpful driving me along, showing me new research, and technically actually building the framework for this test and helping to develop it. And then Garrett as well. Garrett's been with me every step of the way, building and testing all of these different cases. And that's good because, as William Chapman hinted at earlier, testing machine learning models is a pretty complicated affair. So we're going to go over a bunch of different tests for them, but with one primary question motivating all of this, which is just, can we trust or not these machine learning weather emulators? Really with a focus on climate applications. He mentioned that it's a little dubious whether we can use them, especially out of sample for climate. So that's what we're trying to get at in this workshop. Just a quick summary of some of the tests we're going to be doing. Starting off very simple with just a feed in ERA 5 initial conditions and look for mass conservation. You can do that just with checking surface pressure over the entire domain over the simulation. So that's just basic to sort of get ourselves set up. There's not honestly too much interesting analysis I think we can do there, but good to dig our feet in somewhere. And then we get into really the more interesting test cases. So first off, we have a set of steady state initial conditions. Actually, thanks to a student in this room right now, Clement Bouvier, was the originator for these this baroclinic wave initial state. So not sure where you are in the room, but I want to give thanks to you. We're going to be using his initial conditions similarly to like the Ulrich-Bouvier baroclinic wave. So we're going to start off with that initial condition and just see whether or not the model is able to maintain a steady state. That's the whole point of this initialization, is your state should remain constant over time if you don't perturb it. And we'll see later it does not maintain a steady state, but the testing will be about how quickly and sort of realistically does it fall out of that steady state configuration, and looking for any interesting analysis there. We'll also be using another paper that's been mentioned, Greg Hakim's different steady state. It's an era 5 time mean over a 40-year period for the winter season, Northern Hemisphere winter. So it's sort of a smooth background state, and we'll try applying a couple different perturbations and seeing whether we can grow tropical cyclones, baroclinic waves, and a couple other sort of dynamically determined structures. And then finally, we do roughly the same test, which is applying a perturbation to some steady state. But instead of using era 5, we're going to use the actual baroclinic wave, completely analytically determined background. So I'm just going to go through those tests real quick. Like was mentioned earlier, we have 3 different models we're testing: ForecastNet from NVIDIA, GraphCast from Google, and Pangu Weather from Huawei Cloud. Not guaranteed we're going to be able to run all tests on GraphCast, but we'll at least have an intercomparison between ForecastNet and Pangu. There's just some technical difficulties with GraphCast. But like Will said earlier, this is basically, it should be models N. This is basically the operation that all of our models are trained to do. It can be boiled down to something as simple as this. The atmospheric state vector at one time can be determined by the state at the previous time, just fed into this model. So that's the sort of naive framework that we'll start from. And unlike all of the other test cases we've had where we discuss, a sponge layer or what sort of physics parameterizations we're using, we have no options to modify these models at all. So we have a model that we'll try some tests in. And I guess that's the important part. You have to design the test to get at the sort of implicit physics in the model. You can't really turn things on and off to see what they do. So like I said, the first one, I won't go through this too heavily, but conservation of mass says the mass of the atmosphere should not really change. Earth's gravity is not really changing on short time scales. And the area of 1 square meter is not changing. So that's how you calculate pressure, just those 3 variables. So surface pressure on the planet should not change. And we'll just run a simulation to see whether or not global mean surface pressure changes over time. If that does change, it suggests the model is not conserving mass. It's the most likely candidate for why it's changing. So that's the whole plan there. It's a good, simple starter simulation. And then we get into, like I said, the Bouvier et al. Test case. So this is one example of the initial condition. It's in both geostrophic and hydrostatic balance, so it should remain constant in time if run with a dynamical model. And you can see it off to the right here. It's got this symmetrical jet structure, 1 jet in each pole, and then 2 PVU outlined in blue to show you sort of where the stratosphere or the tropopause is. And really what we're looking at here is, we'll actually check the next slide. Will the model maintain a steady state, or does it sort of fall out quickly? And just as a spoiler, these are results I have from doing this experiment last year. Little hard to see, but at the beginning, everything was symmetric across the equator. And over time, you develop asymmetry, and the model, very quickly falls out of a steady state solution. So looking for anything interesting here. One notable feature is the initial condition has no topography. There's no concept of topography in this initialization. But within 24 hours, especially if you look up at T2M, 2-meter temperatures in the top left, you can clearly see a signal of topography. This was really mysterious to us when we first tried this. We were like, whoa, hold on. We said no topography in the initial condition. We plug it in, and now it's got topography. What's going on? And this sort of reframed our thinking for this research. it's not about the initialization for the model, it's about what the model has seen and learned from already. So this model has internalized the concept of topography. It knows the exact height of the surface at whatever lat-lon coordinate you plug in. And no matter what initial condition you give it, it knows what the topography should look like there. So it is just taking your initialization and steering it into exactly what it knows, which is this topography has this effect on temperature and so on. So we're looking for more stuff like this. Yeah, go for it.
Is the temperature perturbation going around every day?
Yep, that's the
Like
diurnal
when
cycle.
The surface heating?
Yeah.
Okay, that's cool.
Yeah, so this is just like a perfect diurnal cycle. And we also said, hey, we never specified solar radiation. Where's this coming from? And that's because it knows the 24-hour diurnal cycle. So there's all of this implicit information that's actually contained in these models. And one of our sort of sub-goals is unpacking that, looking for implicit relationships the model's already developed. So just, yeah, back to this. We're going to be checking how the model falls out of steady state depending on a couple different things. We can change the intensity and location of that jet structure. We can change the virtual temperature at the surface, and we can change the relative humidity profile throughout the atmosphere. So this is our first test that we'll be doing. The second one is going to be, like I said, from Hakim and Massanem 24. They use a 40-year DJF, December, January, February time mean as their initial condition. And sort of importantly, I actually want to highlight this. It's one of the bigger things that made that paper about AI model tests so influential, in my opinion, was that they do not use this naive approach to model stepping, where you say, take time 0, plug it into the model, and look at what comes out. Because when you do that, you get this. You get whatever you started with immediately turns into something that looks like ERA 5. The model was trained on ERA 5 and sort of just seems to quickly return to ERA 5-like conditions. They used what I call tendency reversion for our purposes, but this important part is down here. So dx is the model's 6-hour tendency for some steady state. So you run the model once, that's n of x on a steady state, and this tells you time 1, and you subtract away time 0 to get how much the model changes over a 6-hour window. And every time you step the model forward, you subtract away those tendencies. So if you apply no perturbation to this model, you'll get a steady state in time. You step it forward once, and then you subtract off those same tendencies. And so you should just end up with a steady state. That's actually the test we use to make sure we've implemented tendency reversion properly in the models. Run it with no perturbation and make sure the output stays constant in time. But what Hakim does in his paper is applying an initial perturbation to that state. And so when you subtract off the tendencies, you bring it back to basically where it was before, but it still has the influences of that perturbation. So if that perturbation is, for an example, a baroclinic wave seed, you're going to develop the signal of the baroclinic wave without just falling back into ERA 5. This is what that looks like off to the right here. So this is basically identical to the DJF 40-year mean state, but this is, what is it? This is after, I think, 48 hours or something, maybe 4 days into the simulation. A baroclinic wave was seeded off the coast of Japan, and now we can actually see a very clear structure of a baroclinic wave that's developed through time, but it has not turned into just regular ERA 5 yet. There's not that much noise. So this approach is going to be important for all of our tests throughout DCMIP, basically. You apply some initial perturbation, step the model forward, but make sure to subtract off tendencies so that you can really isolate just how the model responds to that perturbation. And we're hoping to sort of hone in on the dynamics of these different models. So far, the Hakim and Massanem paper,
I was going to ask the perturbation. Is that just initially hit on here, or are you forcing it throughout the entire simulation?
so there are actually 2 different ways to do it. In this one that I show, F is a recurrent perturbation that's applied every time step. So our first experiment is tropical heating, and in that one, every time step you apply something like 1/10 of a degree Celsius of heating to a region, and you just observe the model response. But the other experiments we're going to be doing are just an initial perturbation. So that's for an extratropical cyclone, a geostrophic adjustment experiment, and a tropical cyclone. Good question. Yeah, so we're going to be testing this with all of the models we have. It's going to be interesting. I finished all of the framework to build these tests and deploy them, and I haven't actually analyzed any of these results yet. So part of it is just our group helping me analyze results for my thesis. That'll be convenient. Yeah, so I'm excited to see what we discover. We can also try out different initial conditions, and we can vary the intensity and location of these perturbations to see, is there a perturbation that's too subtle for the model to develop a baroclinic wave response? What if you use a massive perturbation? Does it have what we would think of as a realistic response to it? So all sorts of interesting dynamics questions to be asking here. And that just about covers it for the AI tests.
Yeah, so you see kind of the breadth here, and I bet it was maybe even for some that aren't really from the atmospheric sciences, so maybe too much detail already, yeah. But bear with us, yeah. So our mentors will also help and guide you. In particular, we have, maybe I take one more minute. We are approaching our break here. I take one more minute and click here on our DCMIP page, because we do have a link there which we called workflow. Let's see whether I can bring that up. Here, where's my mouse? So I can launch that already. So this is and I hope everybody had a chance. I haven't looked over the last 2 hours or so whether everybody had a chance to fill out your participants. Let me click on it. To fill out, this is something nice for us all. You know, we kind of see each other. If you are okay with your photo, if you want to upload that, and also you know, provides a little bit of a description. If you want, you could also add maybe your group assignment. Yeah, the group assignment, maybe if you haven't seen it yet, please go to the very bottom here. And this is color-coded. I didn't split up. You see that actually both groups, or I should say all dicores, meaning spectral element, SE or FE3, and also MPAS, which is down here. They have different colors. We did split up those dicore groups into like 2. Yeah, so there are probably 12 or 13 of you in each, not 6 or 7, I should say 6 in those smaller groups, but you are probably 12 or 13 in MPAS and SE and FE3. But we thought it may be a little bit too difficult to manage with 12 people, because you really want to coordinate. You don't want to repeat each other's experiments all the time. Yeah, so take a little bit of time to think about your strategy in your little groups. Hey, you want to do diffusion? I do the variation of the grid spacing, or I do such and such, or I do the modification of the height of the mountain. You want to keep it interesting, yeah, and also this gives you an opportunity to learn from each other. We will communicate, or we will be using this web page. We haven't actually put in a results button yet, I think we probably want to do this over the lunch break. You know, some other button or navigation where you have personal space, or your group. Yeah, maybe we want to split it up by group, and there is personal space for the MPAS group, personal space for FE3, but you can have subspaces, you know, your own space. And this is what will be a way to communicate everything with each other. All right, I think I only have one more minute. We also hit upon this tomorrow, yeah, a little bit going over also visualization options that we have pointed out a little bit. Check it out also tonight if you like. Okay, so let me maybe finish with a couple of comments here on the workflow. And you will be, this is just a heads up, there will be cloning cases we already created. It is way too complicated, or we thought it's way too complicated, not that you can't do it, to create everything from scratch, because there are so many little details for these analytic initializations. This is we are doing things that are not out of the box for the NCAR model, yeah? And therefore we have very specific, and this is even DICOR-specific implementations and variations of the source codes, and that would be very difficult to do, so we don't do that. We created everything nice and clean. You can also learn how to do it later during the week, but the way to go after is actually a command which is called clone. Here you see it. It's actually, let's see, create clone. Here's a command. So you are cloning cases from us, and they have all the modifications. They have nameless settings, initial nameless settings. But at that point, feel free. After you cloned it, it's yours. Yeah, you can change source code. You can change nameless. You can change run length, whatever. Yeah, and this could be in collaboration with your mentors. There is also a lot of extra information about CSM in general, and CAM also on those lower click options. For example, more explanations what the nameless options are. Yeah? But this would be too much information right now. Yeah? So just let's start gentle today. And you also see the matrix here. And this matrix gives you all the information for the clones. So you see when you clone it, you see some of those placeholders. And you will need kind of the names here from the matrix to collect the information for your specific configuration. Again, you want to split up in your groups and make a strategy. Maybe on the web page you agree on a strategy. Hey, who's doing what? Today we are probably all learning how to do this. Yeah, maybe there's not too much strategy today. Yeah, we want to all compile the model. We just learned that we had a problem already on the Casper machine, that the Scratch system overheated. We changed this, and maybe for mentors in the room, we changed this now to a different directory, so a different, we can't use Scratch space, that's offline, but we have we have space on late work. Everybody has 2 terabytes, that should be enough, I think, for the purpose of this. But just note Scratch space. If you see Scratch someplace, it's not available at the moment. Sorry. Okay, so that's kind of how it goes. This walks you through how to do the executable, which is case build, and how to submit this. And today we want to be gentle with lower resolution, things that finish in a few minutes, basically, and don't use as much compute. And then there is regridding information. Some of these models, well, they're all not on lat-long grids. So we do recommend, which isn't a must, we also can use visualization on native grids, CubeSphere grids, or hexagonal grids with a Python tool called UXArray. Our current guides here are not for that, but our interpolated data. So there's information how to interpolate from a CubeSphere to a lat-long grid. But that's not a must later, maybe during the week. Yeah, especially Colin will tell you that you should do that. Yeah, once he's here on Wednesday. Yeah. Okay, maybe that's it for now. Let's break and have lunch. Lunch is, well, just follow the crowd. Yeah, and then we reconvene in an hour at 12:45ish, 1:45ish in the library. All right.